Good morning, guys. Today is our day 13 of restart session 1 physics. So, basically, we are done with two examinations of both. So, English and chemistry are done. Hope every one of you might have done well. So, இப்போ நம்ம நடந்ததை பற்றி யோசிக்காமல் even if it didn't go well, we will not care about that. We'll move on towards the next three subjects. Yes. So for next we are stepping onto physics board examination, which is 5 days away from now. So, so first things first, let's get to know about the syllabus, and then we'll get started with our today's session. Just wait a minute. So yes, there you go. So இதுதான் நம்மளோட syllabus for our theory part of this particular examination. So electrostatics, so நமக்கு டோட்டலாக 9 யூனிட்ஸ் இருக்குது and we have about 14 chapters. Yes, so first unit is electrostatics, which combines of electric charges and fields, and then we have electrostatic potential and capacitance, and then current electricity அப்படின்றது ஒரு தனி யூனிட்டாக கிளாஸிஃபை பண்ணியிருக்காங்க. ஸோ தீஸ் ஆல் புட் டுகெதர், அதாவது இந்த எலக்ட்ரிசிட்டின்ற பர்டிகுலர் டாபிக் ஆல் புட் டுகெதர் இட் கம்ப்ரைசஸ் ஆஃப் 16 மார்க்ஸ். ஸோ மூவிங் டவுன் வி ஹவ் மேக்னெட்டிக் எஃபெக்ட்ஸ் ஆஃப் கரண்ட் அண்ட் மேக்னட்டிசம். அதில் வந்துட்டு வி ஹவ் மூவிங் சார்ஜஸ் அண்ட் மேக்னட்டிசம் அண்ட் மேட்டர். அண்ட் தென் அதுக்கப்புறம் வி ஹவ் யூனிட் 4, தட் இஸ் எலக்ட்ரோ மேக்னெட்டிக் இண்டக்ஷன் அண்ட் ஆல்டர்னேட்டிங் கரண்ட். இந்த ரெண்டு சாப்டர்ஸும் ஸோ ஆல் தீஸ் புட் டுகெதர் இந்த மேக்னட்டிசம் அப்படின்ற பார்ட் வந்துட்டு வி ஹவ் அபவுட் 17 marks. And then we'll enter into electromagnetic waves, where we'll electromagnetic waves we'll have electromagnetic waves, that one particular chapter. I think we have done this particular chapter already. Nonetheless, we'll try covering it as well. Yes. And optics அப்படின்றது it's going to be a very big unit. Yes, so அதில் we'll have ray optics and optical instrument என்ற ஒரு chapter, and then we have wave optics, and then we'll have which is comprising of 18 marks. So the major 3 units electrostatics based பண்ண யூனிட்ஸ், அதாவது எலக்ட்ரிசிட்டி, மேக்னட்டிசம், அதுக்கப்புறம் வந்துட்டு இந்த ஆப்டிக்ஸ், இதுதான் வந்துட்டு மேஜர் 3 யூனிட்ஸ். ஸோ இதில் கம்பைன் பண்ணி we have about 51 marks. So and then moving down we have dual nature and radiation, அதாவது மாடர்ன் ஃபிசிக்ஸ்ன்றாங்க. மாடர்ன் ஃபிசிக்ஸில் we have dual nature, radiation, atoms, nuclei. இந்த சாப்டர்ஸ் எல்லாமே டோட்டலாக சேர்த்து கம்பைண்டாகவே we will have 12 marks only. And then finally நம்ம செமிகண்டக்டர்ஸில் ஒரு பர்டிகுலர் சாப்டர் it has the highest weightage of about 7 marks. Yes, ஸோ நம்மளுடைய ப்ரைமரி டார்கெட் இப்போது என்னவா இருக்கலாம்? ஆக்சுவலாக ஃபிசிக்ஸை பொறுத்த வரைக்கும் if we go in order it would be better, but hope you have all done all the chapters already. At least you know something about each chapter. So it would be better if we cover ஒவ்வொரு யூனிட்லேருந்தும் ஒரு chapter in a day. Like if I am starting with electric charges and fields today, and then from that particular electricity part, from magnetism part we will start with moving charges and magnetism, so that we will have a balance. இது வந்துட்டு நான் என்ன சொல்கிறேன்னா, we will have to do it in the same day. And then modern physics ஒரு chapter. Semiconductors, I think you will all have done it already, but nonetheless we will do it as well, and according to our plan. So basically அதில் சில remembrance part இருக்குது, right? So that's it. That's the 70 marks denomination, complete denomination of how we are gonna write our examination. And then நம்மளுடைய சப்டாபிக்ஸ் நான் பார்க்கலாம். ஸோ சப்டாபிக்ஸை பொறுத்த வரைக்கும் இப்போ நான் எல்லாத்தையுமே கவர் பண்ண மாட்டேன். ஒவ்வொரு சாப்டர் நம்ம ஆரம்பிக்கிறதுக்கு முன்னாடி நான் அந்த சப்டாபிக்ஸ் எல்லாத்தையும் டிஸ்பிளே பண்ணிவிட்டு அதுக்கப்புறமா I will get started with the chapter, because we do not have much time to read all the subtopics at that time. Do we have anything else? Okay, so hopefully you will all have done the practicals examination, and that's for 30 marks. What else do we have? Yeah, that's all about it. O- ஓகே, ஸோ இப்போ வந்துட்டு நம்மளோட கொஷின் பேப்பர் டிசைன் எப்படி இருக்குது அப்படின்றத பார்ப்போம். ஸோ ரிமெம்பரிங் பார்ட் அண்ட் அண்டர்ஸ்டாண்டிங் பார்ட் இது ரெண்டும் கம்பைன் பண்ணி, அதாவது சில ஃபார்முலா பேஸ்டு டெஃபினிஷன் பேஸ்டான விஷயங்கள் எல்லாத்தையும் கம்பைன் பண்ணி வில் ஹாவ் அபவுட் 27 மார்க்ஸ். ஸோ ரீடிங் என்சிஆர்டி line by line and try to remember, understand and remembering அப்படின்றது இட்ஸ் going to be really really important aspect. So that holds about 27 marks. மற்ற பார்ட்டில் கூட you will have knowledge, but இதில் பொறுத்த வரைக்கும் you will have to remember. Okay, that's really important. Fine. So applying part we will have about 22 marks, and then we have analyzing, evaluating and creation part, in which we'll have to encounter a variety of questions. We'll have to analyze the situation, and accordingly we'll have to use our knowledge to solve the particular question. Okay, so that's how this particular question paper design is gonna be. And then what else do we have? Okay, so பெருசாக எதுவும் இல்லை. Yes, so we'll get started with the first chapter itself to begin with. So I think it would be easier in Rodhuda. It would be better if we start from the basics so that we can build up upon it. So first chapter is going to be electric charges and fields. ஸோ நான் என்ன பண்ண போகிறேன் அப்படின்னா, இந்த ரேஷ்னலைஸ்டு புக்கை யூஸ் பண்ணுறதா இல்லை. ஸோ பிகாஸ் rationalized book has a lot of things deleted, so we'll make use of our previous books like 2018-19 editions or 20th editions. Yes, so that it will be better in the session only. It will be helpful for our mains purpose also, mains and advanced purpose. So let's see the topics: electric charges, conservation of charge, Coulomb's law or force between 2 point charges, and then we have force between multiple charges, and then superposition principle. இது எல்லாமே வந்துட்டு it will talk about the attributes of charges. And then moving on, we'll have certain thing called as electric field. In a force அப்படின்ட்டு இருந்தால் we'll have something called as field, conservative field, something like that. And then we'll have electric field due to every single objects like a point charge, and then we'll define what are electric field lines, what are their properties, and then we'll get into electric dipole, what is a dipole and what is its electric field and the torque on a dipole, and we'll have potential energy as well if it is placed in a uniform magnetic field. And then we'll talk about electric flux and Gauss's theorem, and then by using that particular thing we'll try finding the field due to infinite long wire, infinitely uniformly charged, infinite plane sheet and thin spherical shell. அதாவது மூணு ஆப்ஜெக்ட்ஸ் மட்டும் தான் கொடுத்துருக்காங்க. ஒன் லாங் வயரு, இன்னொன்று சார்ஜ் இன்ஃபைனைட் பிளேன் ஷீட்டு, அண்ட் தென் வில் ஹாவ் thin spherical shell. And I think they have even used solid spherical shell. எஸ், ஸோ நம்ம ஃபஸ்ட்டு ப்ரைமரியில் இந்த பர்டிகுலர் டாபிக்ஸை ஃபர்ஸ்ட் திங்ஸ் ஃபர்ஸ்ட் கவர் பண்ணிடுவோம், அண்ட் தென் வீல் என்டர் இன் டு சம் அதர் டாபிக்ஸ் இஃப் டைம் பர்மிட்ஸ். ஸோ நம்மளோட சீக்வன்ஸ் எப்படி இருக்க போகுதுன்னா, வீல் ரீட் என்சிஆர்டி, வீல் ட்ரை அண்டர்ஸ்டாண்டிங் தெம், and then we'll solve questions based on that particular parts. Yes, so let's get started with our first topic of the day. So yes, let's get started with the first chapter of the day, electric charges and fields. So introduction, all of us have the experience of seeing a spark or hearing a crackle when we take off our synthetic clothes or sweater, particularly in dry weather. So this is almost inevitable with the ladies' garments like a polyester sari. Have you ever tried to find an explanation for this phenomenon? Another common example of electric discharge is the lightning that we see in the sky during thunderstorms. We also experience a sensation of an electric shock either while opening the door of a car or holding the iron bar of a bus after sliding from our seat. So the reason for these experiences is the discharge of electric charges through our body, which were accumulated due to the rubbing of insulating surfaces. So you might have also heard that this is due to the generation of static electricity, precisely the topic that we are going to see and discuss today. The static means that it does not move with time, and electrostatics deals with the study of forces, fields, and potentials arising from static charges. So first of all, they have given us some certain examples in which we have encountered the presence of static electricity, such as lightning, and then the one in which if I'm அதாவது ஒரு இன்சுலேட்டிங் சர்ஃபேஸோட ரப் ஆகும்பொழுது ஒரு டைப் ஆஃப் ஸ்டாட்டிக் எலக்ட்ரிசிட்டி இண்டக்ஷன் அண்ட் அது காரணமாக ஒரு சின்ன ஒரு எலக்ட்ரிக் ஷாக் எக்ஸ்பீரியன்ஸ் உங்களுக்கு கிடைக்கும். அந்த மாதிரி சில எக்ஸாம்பிள்ஸ்லாம் கொடுத்து we are going to get started this chapter. So basically I'm just trying to lay a foundation of, I'm just giving you a glimpse of what's going to happen in this particular chapter. So we'll talk about the forces, fields, and then the potentials arising from the static charges. Moving down, let's see what an electric charge is. So historically, the credit of discovery of the fact that amber rubbed with wool or silk attracts light objects goes to Thales of Miletus of Greece around 600 BC. The name electricity is coined from the Greek word electron, meaning amber. So many such pairs of materials were known which on rubbing could attract light objects like straw, with balls and bits of papers. We can perform the following activity at home to experience such an effect. Cut out a long thin strip of white paper. Okay, fine. Just observe that if two glass rods rubbed with wool or silk cloth are brought close to each other, they repel each other. அதாவது என்ன சொல்ல வராங்கன்னா, two rods, glass rods, if I'm rubbing with a silk cloth and if I'm bringing together these particular rods, they are repelling each other. So two strands of wool or two pieces of silk cloth with which the rods were rubbed also repel each other. However, the glass rod and wool attracted each other. Okay, can you understand what's happening over here? Similarly to plastic rods rubbed with the cat's fur repelled each other but attracted the on the fur. On the other hand, the plastic rod attracts the glass rod and repels the silk or wool with the glass rod is rubbed. So the glass rod repels the fur. So it might be a little confusing, but as we go with the flow, I hope you will all understand. And just reading it, there's nothing much to explain. Okay, so if a plastic rod rubbed with fur is made to touch with two small pith balls, nowadays we can use polystyrene balls suspended by silk or nylon thread, then the balls repel each other. Great, and are also repelled by the rod. A similar effect is found if the pith balls are touched with a glass rod rubbed with silk. A dramatic observation is that a pith ball touched with a glass rod attracts another pith ball touched with a plastic rod. So can you find what's happening? ஆக்சுவலாக வந்துட்டு ஒரே டைப் ஆஃப் மெட்டீரியலோட ரப் பண்ணி அந்த பர்டிகுலர் டைப் ஆஃப் மெட்டீரியல்ஸை பக்கத்தில் கொண்டு வரும்போது தேர் ட்ரைங் டு ரிப்பல். அண்ட் அதுவே இஃப் ஐம் பிரிங்கிங் டூ டிஃப்ரெண்ட் மெட்டீரியல்ஸ் கம்ப்ளீட்லி விச் ஆர் ஹேவிங் கம்ப்ளீட்லி டிஃப்ரெண்ட் ஆஸ்பெக்ட்ஸ். ஸோ ஆஸ் வி கேன் see over here, a glass rod is attracted towards a plastic rod, whereas this plastic rod is actually repelling away from the woolen cloth, whatever the thing is. And similarly, as you can see, the pith ball touched with the glass rod is actually attracting another pith ball touched with a plastic rod and not with a glass rod. Glass rod touch ஆனதோட ரிப்பல் ஆகுது, பிளாஸ்டிக்கோட டச் ஆனதோட அட்ராக்ட் ஆகுது. So the seemingly simple facts were established from years of efforts and careful experiments and their analysis. It was concluded after many careful studies by different scientists that there were only two kinds of an entity which is called the electric charge. So அதாவது ஃபைனலாக they are coming to a conclusion is that there is something basic. If I'm breaking down all these phenomena, there is something basic that's occurring, and there are two entities for that particular thing, and they are defining it as electric charge. We say that the bodies like glass or plastic rods, silk, fur, and pith balls are electrified. So which means that they acquire an electric charge on rubbing. So the experiments on the pith ball suggested there are two kinds of electrification, that is like charges repel and unlike charges attract each other. The experiments also demonstrated that the charges are transferred from the rods to the pith balls on contact. They said that the pith balls are electrified on or are charged by contact. So basically, there's some amount of charge transfer occurring. Yes, so and they are concluding that like charges are going to repel and unlike charges are going to attract, and these are the results of what electrification of the speed with balls have given us. That's what we have concluded over here. So the property which differentiates the two kinds of charges is called the polarity. அதாவது ஒரு பர்டிகுலர் சார்ஜை டிஃபரன்ஷியேட் பண்ணக்கூடிய அந்த பர்டிகுலர் எலிமெண்ட் அதோடைய டெஃபினேஷன் என்னன்னா தட்ஸ் polarity. So the property which differentiates the two kind of charges. So when a glass rod is rubbed with silk, the rod acquires one kind of charge, the silk acquires the second kind of charge. This is true for any pair of objects that are rubbed to be out. Now if the electrified glass rod is brought in contact, general type was electrified contact with the silk or whatever something it was rubbed with. Now again there is no attraction or repulsion occurring, which means that there is a charge redistribution occurring as they come in contact. Since this guy has a, let's say this guy has a negative charge and this guy has a positive. So as I'm bringing them in contact, finally they attain their neutrality and then no attraction or no repulsion is occurring. So thus the charges occurred after rubbing are lost when the charges are brought in contact. Neutralize or nullify each other's effect. Therefore the charges were named as positive and negative. So அதாவது இந்த nullifying அப்படின்றது அந்த ஒரு பர்டிகுலர் டெர்மினாலஜி வந்துட்டு நம்மளோட மேத்தமெட்டிக்ஸில் தான் பார்த்துருக்கோம். ப்ளஸ் ஒன் வந்துட்டு it nullifies -6. ஸோ அது matter is going to be negative. So to get to 0. This might have been the philosophy in naming the charges are positive and negative. By convention, the charges on glass rod or cat's fur is called positive, and on plastic rod or silk is called termed as negative. So according to NCERT, what they're trying to say is that அதாவது கிளாஸ் ராட்ல அக்கேர் ஆகிற அந்த பர்டிகுலர் சார்ஜோ இல்லைனா கேட்டோட ஃபரில் அப்பான் ரப்பிங் கேட் ஃபர் பிளாஸ்டிக் அப்படின்ற எக்ஸாம்பிளில் அக்கேர் ஆகிற சார்ஜஸ் பாசிட்டிவ் சார்ஜ் அண்ட் அல்லது சில்க் க்ளோத்தில் வந்துட்டு அக்கேர் ஆகிற சார்ஜஸ் பண்ண போய் நெகட்டிவ். So if an object possesses an electric charge, it is said to be electrified or charged. When it has no charge, it is said to be neutral. So basic outcomes என்னன்னா, அதாவது there is some entity called charge, which basically like charges அப்படின்றது there are two kind variants. So like charges repel and unlike charges gonna attract, and an object is said to be electrified or charged if at all if it has an electric charge, and if it doesn't have any charge then it is said to be neutral. By convention we have certain factors. So that's all about it. Now they have given certain blue box. Okay, so basically they'll talk about how electricity and magnetism was unified together, and in the later chapters of our class 12 syllabus we will talk about how electricity, magnetism and optics are all combined together, and finally how energy was all conserved அப்படின்ற மாதிரி என்ன ஒரு பர்டிகுலர் ஒரு டிஸ்கஷன். It will not be I'm not gonna read this. Actually I've read it already and I don't think it would be useful now. Yes, so as we go further we ourselves can see what's actually happening, how electricity and magnetism are all combined together. So a simple apparatus to detect charge on a body is the gold leaf electroscope. So we are going to talk how I'm going to detect charge அப்படின்றது. ஸோ சார்ஜ்ன்றது என்னன்னு பார்த்தாச்சு இல்லையா. ஸோ அடுத்து டிடெக்ஷன் அண்ட் அதில் ஒரு சிம்பிள் apparatus வந்துட்டு the gold leaf electroscope. It consists of a vertical metal rod housed in a box with two thin gold leaves attached to its bottom end. When a charged object touches the metal knob, so then the topல இருக்க the metal knob, so let me just show the picture. So the topல இருக்க metal knob இருந்து the charge. So if according to the used for seeing interaction for this. Okay, you notice that two halves move apart. This shows that the strip has acquired charge on iron. When we fold it into half, both halves have the same charge. Okay, hence they repel each other. So the same effect is seen in the leaf electroscope. And charging the curtain rod by touching the ball end with an electrified ball, as is transferred to the curtain rod and attached film aluminum foil. Both the halves of the foil get similar charge and therefore repel each other. The divergence in the leaves depends on the amount of charge on them. Let us first try to understand why material bodies acquire charge. Okay, so basically we have seen what is the mechanism, why is it happening. Now, now let's try understanding how material bodies are acquiring charges. So you know that all matter is made up of atoms or molecules. Although normally the materials are electrically neutral, they do not contain charges, but the charges are exactly balanced. So most of the bodies are electrically neutral அப்படின்ற பட்சத்துலையும் there are charges but they are actually nullifying each other, or it means that they are exactly balanced. Forces that hold the molecules together, forces that holds atoms together, the adhesive force of a glue, forces associated with surface tension, all are basically electrical in nature, arising from the force between charged particles. So இப்போ நம்ம பார்க்குற most of the cases of forces of binding to some two objects அப்படின்றது it is all fundamentally molecular level. It's gonna be based upon the electrical it's gonna be electrical in nature அப்படின்னு சொல்லிட்டாங்க, and it is arising from the forces between the charged particles. So thus the electric force is all pervasive, encompasses almost each and every field associated with our life. It is therefore essential that we learn this. And here we go, we have the answer over here. So basically each and everything that we see, that we encounter in our life, are all comprised of this particular electric force. And yeah, it is therefore essential that we learn more about such a force. So to electrify a neutral body, we need to add or remove one kind of charge. So when we say that a body is charged, we always refer to this excess charge or deficit of charge. In solid, some of the electrons being less tightly bound in the atom are the charges which are transferred from one body to the another. So a body can thus be charged positively by losing some electrons, and similarly a body can be charged negatively by gaining some electrons. When we rub a glass rod with a silk, some of the electrons from the rod are transferred to the silk core. Thus the rod gets a positive charge and the silk gets a negative charge. So no new charge is created in the process. Yes, so it's an obvious factor that there's no new charges being produced, and also the number of electrons that are transferred is a very small fraction of the total number of electrons in the material body. Also only the less tightly bound electrons in a material body can be transferred from it to another body by rubbing. So therefore when a body is rubbed with another, the bodies get charged, and that's why we have to stick to certain pairs of materials to notice charging on rubbing of the bodies. So yeah, basically you can see what's actually happening, and why and how the material bodies are acquiring charges. Actually they have not given much. So actually until the particular body, if it is acquiring a charge, it can acquire a positive charge, a negative charge, and we have seen certain examples where rubbing is one of an example of how a body gets charged. Like rubbing of a glass rod by a silk cloth. The silk cloth is obtaining a negative charge due to the electrons movement from the glass rod towards the silk cloth, and similarly the glass rod is obtaining a positive charge, and there is no new charges being created. Yes. So moving down, we'll talk about conductors and insulators. A metal rod held in hand rubbed with wool will not show any sign of being charged. However, if a metal rod with a wooden or a plastic handle is rubbed without touching its metal part, it shows a sign of charge. Suppose we connect one end of a copper wire to a neutral pith ball and the other end to a negatively charged plastic rod. We will find that the pith ball acquires a negative charge. So if a similar experiment is repeated with a nylon thread or a rubber band, no transfer of charge will take place from plastic rod to the pith ball. Why does the transfer of charge not take place? So let's see that we'll have to know about the type of material, what it is actually. So some substances readily allow passage of electricity through them, others do not. Those which allow the electricity to pass through them easily are called conductors. They have electric charges that are comparatively free to move in the material. Metals, human and animal bodies, and earth are conductors. Most of the non-metals like glass, porcelain, plastic, nylon, wood offer high resistance to the passage of electricity through them. They are called insulators. Most substances fall into one of the two classes stated above. So what else do we have? Actually we have something else as well. We have something called the semiconductors. Is when some charge is transferred to a conductor, it readily gets distributed over the entire surface. In contrast, if some charge is put in an insulator, it stays at the same place. So if you want this particular part, we will just remember it for now. If I am putting certain amount of charge, it's gonna get redistributed in that whole of the medium. Yes. So we'll see why is it happening. So this property of the materials tells you why a nylon or a plastic comb gets electrified on combing dry hair or on rubbing, but a metal article like spoon does not. So the charges on metal leak through our body to the ground as both are conductors of electricity. So I hope we are the effects of getting charged vantu we will be able to see in insulators like a comb which is made of plastic or something like that, essentially not in metal. And if I'm you having certain metallic body and if I'm trying to charge it, I will not be able to see any amount of charge electrification. It is not because that they are not getting charged, but the charges are actually passing through our body, which is a conductor, through the to our earth, which is also a conductor. So when we bring a charged body in contact with the earth, all the excess charge on the body disappears by causing a momentary current to pass through the ground through the connecting conductors such as our body. This process of sharing the charges with the earth is called grounding or earthing. So basically in the particular process என்ன பண்ணுறோம், ஒரு particular body, I am a body அப்படின்னா I have certain amount of charge அப்படின்னா there will be some amount of momentary current creation such that the excess amount of charge will pass through my body towards earth. So this particular process is called grounding. Earthing or grounding. Earthing provides a safety measure for electrical circuits and appliances. A thick metal plate is buried deep into the earth and thick wires are drawn from this plate. These are used in buildings for the purpose of earthing. The electric wiring in our houses has three wires. One is the live, other one is a neutral, and then we have an earth wire. So I think yes, as you can see, this is a typical plug in which I have an earth wire, a live wire. I don't know which one is live wire, and the other one is yes, neutral wire, and this is earthing wire. So the first two carry electric current from power station, and the third is earthed by connecting it to the buried metal plate. ஸோ ரெண்டு வயர்ஸ் வந்துட்டு இட் வில் பி கனெக்டட் டைரக்ட்லி டுவர்ட்ஸ் த நம்மளோட கரண்ட் சோர்ஸ்லேருந்து வர it will be directly connected towards the current source. The third wire it will be connected towards actually to our metals that we have buried underground. So metallic bodies of the electric appliances such as electric iron, refrigerator, TV are connected to the earth wire. So when any fault occurs or live wire touches the metallic body, the charge flows to the earth without damaging the appliance and without causing any injury to the humans. So the basic principle is that if at all if an excess charge is produced, then obviously a high amount of force will be present, which means that it can damage our appliances. And to avoid that, we are basically making use of this particular earthing, which the excess of charge is basically flowing to the ground. Yes. So this would have otherwise been unavoidable since the human body is a conductor of electricity. Yes. So yeah, actually we have not yet started with the chapter, but now itself I'm feeling a bit dizzy. Yeah, we have already done half an hour. I don't think this is the pace we should go with. I think we should speed up 1 minute. enter. Okay, fine, great. On the distance, yes, we know that the opposite charges attract while similar charges repel. However, the magnitude of force depends on the distance between the charges, and in this case, the force of attraction overweighs the force of repulsion. As a result, the particles, like bits of paper or pith balls, being light or pulled towards the rods. Okay, fine. So we have seen another method of how charges are getting induced. So basically, in this particular method, நமக்கு charge induction அப்படின்றதுல there is no transfer of charges occurring. So basically what we are trying to do is that we are bringing near some one type of a charge near a particular spherical surface, and then automatically the other type of charge is induced in the nearest proximity of that particular other surface, and which means that upon removing this particular charge, I am basically accumulating the negative charge or positive, whatever the opposite type of charge that's been present in the whole of the system. Yes, so that's what actually happens, and that's how the things are gonna get charged. So how can you charge a metal sphere positively without touching it? Okay, so they've asked a question. We'll have to charge a metallic sphere. So let's say I have a metallic sphere. Yes, shows an uncharged metallic sphere on an insulating metal stand. Bring a negatively charged rod close to the metallic surface as shown. As the rod is brought close to the sphere, the free electrons in the sphere move away due to repulsion and starts piling up at the farther end. The near end becomes positively charged due to deficit of electrons. This process of charge distribution stops when the net force on the free electrons inside the metal is zero. அதாவது when this particular net force is trying to become zero, then equilibrium is attained and this particular charge distribution occurs until that particular neutralization is occurring on forces. So the electrons will flow to the ground while the positive charges at the near end will remain held there due to the attractive forces. The positive charge continues to be held at the near end. Remove the electric electron. So basically, we are seeing how an induction is taking place in a particular type of a system. Every induction மூலமாக charge induction, charge induce பண்ணுறோம் அப்படின்றத பார்ப்போம். So in this experiment, the metal sphere gets charged by the process of induction and the rod does not lose any of its charge. Similar steps are involved in charging metal sphere negatively. So in this case, the electrons will flow from the ground to the sphere when the sphere is connected to the ground with a wire. Okay, they have said that when I am trying to make it negatively charged, I will have to bring a positive charge thing. And okay, basically in an electric field, electrons will move in the opposite direction of the field. And as I am bringing a positively charged material or rod near to the metallic sphere, which means that I am creating a field in the particular sphere, which means that the intensity of field becomes higher. Am I saying it right? Or am I missing something? Actually, we will see this particular topic in detail in the upcoming pages. Yes. So basic properties of electric charge. So now we are going to see certain basic properties. So எப்பவுமே charges when we are discussing, we will treat them as point charges. First things first, we will talk about additivity. So basically, additivity is that if a system contains n charges, Q1, Q2, Q3, the total charge of the system is the sum of n charges. So the sum is such that it comes with a positive sign if it is a positively charged particle, and if it comes with a negative sign if it is a negatively charged particle, whatever. And it does not have any direction. It's basically a scalar like mass, but mass has only one variant, but charges have two variants. And then we have the electric charges being conserved. So charge we have seen in case of transfer of electrons itself, and the particular case la பார்க்கும்போது charges only creation and destruction எதுவும் நடக்கல. In the particular amount of charges moving towards other body or something like that. So basically, a transfer of charge, a transfer of electrons does not need any charge for creation, or it doesn't happen actually. So picture of particles of electric charge enables us to understand the idea of conservation of charge. When we rub two bodies, what one body gains in charge, the other body loses. Within an isolated system consisting of many charged bodies, due to interaction among the bodies, charges may get redistributed, but it is found that the total charge of the isolated system is always conserved. So அதாவது ஒரு ஐசோலேட்டட் சிஸ்டமில் நிறைய சார்ஜ் பாடிஸ் இருந்தாலும் இந்த particular interactions in காரணமாக the net charge will always be conserved. Say if I am taking an isolated body, isolated system with a positive charge or something like that, plus 1 charge or plus 2 charge, something like that, and in that particular scenario the total charge of that particular system will always be conserved. Nevertheless, what will happen inside the system? So it is not possible to create or destroy a net charge carried by any isolated system. So it is actually possible that a neutron can turn into a proton and electron, but nonetheless they are actually having an equal and opposite charges, which means that the total charge will be before and after will be a zero factor. Yes. Moving down, we will talk about quantization. So basically the electric charge is basically quantized, and it is an integral multiple of the basic unit of charge, that is denoted by E. So that's the charge Q on a body is always given by Q is equal to N, where N can be an integer, can either be a positive integer or negative integer, which means that by convention that an electron possesses a charge of minus E, the basic unit, and whereas a proton consists of a charge of plus E. So that's what we call as a quantization of charge. Okay, so basically the quantization was first suggested by the experimental laws of electrolysis done by Faraday. It was experimentally demonstrated in 1912 by Coulomb. So now we'll talk about the charge, the unit of charge, its measurement, how we are going to denote it. So basically the unit of charge is actually called as Coulomb. Yes, a Coulomb is defined in terms of the unit of electric current. Okay, fine, which we'll learn in the next chapter in series, which means 1 coulomb is the charge flowing through a wire in 1 second if the current is 1 ampere. So which means that basically according to electric current, I is equal to Q by T, and according to this particular definition, Q is equal to IT, which means that 1 coulomb of charge is the charge flowing in 1 second if the current in that particular wire flow is 1 ampere. Yes, that's Coulomb. We'll denote it by a symbol C. Moving down, the basic unit of charge is 1.6 into 10 power minus 19 coulombs. Thus, there are 6 into 10 power 18 electrons in a charge of minus 1 coulombs. So, how am I just deriving it? So, basically, if 1 electron possesses a charge of 1.6 into 10 power minus 19 coulomb, one coulombla how much is basically a linear concordance. So with that particular thing, I'll basically have the reciprocal of this 1 by 1.6 into 10 power minus 19, and it turns out that 1 coulomb of charge will be constituted by 6 into 10 power 18 electrons. Yes, that's for minus 1 coulomb, and for plus 1 coulomb it's going to be 6 into 10 power 18 protons. So in electrostatics, charges of this large magnitude are seldom encountered, hence we'll use smaller units like micro or millicoulomb, something like that. So if the protons and the electrons are only basic charges in the universe, all the observable charges has to be an integral multiple. So thus if a body contains n1 electrons, n2 proton, then it's going to be n2 minus n1 times E. So since n1 and n2 are integers, the differentials should also be okay, fine, great. The step size is however very small, because at the macroscopic level we deal with the charges of a few microcoulomb. At this scale, the fact that the charge of a body can increase or decrease in units of E is not visible. The grainy nature of the charge is lost and it appears to be continuous. That basically, when I'm seeing in a macroscopic level, it basically seems that the charges are continuous, but actually it is consisting of single charges, minute charges arranged according to that particular scale or whatever it is. So this situation can be compared with the geometrical concepts of points and lines. A dotted line viewed from a distance appears continuous to us, but is not continuous in reality. As many points are very close to each other, they normally give an impression of continuity. Many small charges taken together appear as a continuous charge distribution. At the macroscopic level, one deals with the charges that are enormous compared to the magnitude of charge E. So for example, the magnitude of charge E is actually 1.610 power minus 19 coulomb. That's about a charge of magnitude, say 1 microcoulomb, is actually 10 power 13 times the electronic charge. So macroscopic level, this is not the actual charge that we are going to deal with. So at this scale, the fact that charge can increase or decrease only in units of E is not very different from saying that charge can take continuous value. Thus at the macroscopic level, condensation of charge has no practical consequence and can be ignored. The microscopic level, where the charges involved are of the order. So basically, சொல்ல வராங்க அப்படின்னா, in a macroscopic level, in a day-to-day scenario பொறுத்த வரைக்கும், when I'm talking about charges, it's not gonna be that it will be, அதாவது let's say I have a charge of about 1 coulomb. I mean, not 1 coulomb, it's ஒரு basic unit of charge இருக்குன்னு வச்சுக்கோ, that's 1.6 into 10 power minus 9. And if at all, if there is another system which has 3 coulomb, then it should be emphasized that quantization of charge has to be carried out. But in case if I'm saying it on macroscopic level, பொறுத்த வரைக்கும், say I'm dealing with 1 microcoulomb. ஒரு microcoulomb is considered to be lowest amount, the least amount in which we are basically measuring, and the particular amount is turning out to be 10 power 13 times the basic charge அப்படின்ற பொழுது, at macroscopic level, the quantization of charge and its practical consequences can be ignored அப்படின்றத சொல்லலாம். ஸோ இந்த ஸ்கேல், நம்ம எந்த ஸ்கேலில் எந்த லெவலில் வந்துட்டு நம்ம சார்ஜஸை பற்றி டிஸ்கஸ் பண்ணுறோம் அப்படின்றது இஸ் கான் டு பி an important fact. So 10 power 9 electrons move out of a body to another body every second. How much time is required to get a total charge of 1 coulomb on the other body? So basically 1 coulomb ante it's a constituents of 6 into 10 power 18 electrons, and I have 10 power 9 electrons moving per second. So which means that the total number of electrons required by electron moving per second, so that's a 6 into 10 power 9 seconds. I think that's how they're actually calculating it, and that's about 200 years it seems. So 1 coulomb is therefore a very large unit for many practical units. They are actually trying to emphasize how big 1 coulomb is. Even if 10 power 9 electrons move out of a body, it will take about 200 years for that particular body to obtain a charge of 1 coulomb. So how much positive and negative charge is there in a cup of water? Okay, great. They are trying to ask. So let us assume that mass of 1 cup of water is 250 gram. So basically they are assuming that there is a 250 gram of water. The molecular mass of water is 18 gram, which means that 1 mole, which is about 6 into 10 power 23 molecules, is 18 gram, and therefore the total number of molecules is going to be the total number of moles, that is 250 by 18 into the Avogadro number 6 into 10 power 23. So as I do these particular calculations, each molecule of water contains 2 hydrogen and 1 oxygen atom, that is 10 electrons and 10 protons, which means that for calculation of the total negative charge, it will be basically a multiplication of another 10. I mean, we'll first multiply the unit of charge for 1 electron or 1 proton respectively, and in 1 H2O molecule we'll have about 10 electrons or 10 protons accordingly, and then upon finally by obtaining this particular multiplication, we'll obtain the total net charge present in 1 cup of water. Yes, so basically we have made an assumption that it is about 250 grams. Yes, and also the charge of 1 basic unit is considered to be 1.6 into 10 power minus 19 coulomb, and with that we'll conclude our properties of charges, and then we'll move on towards the Coulomb's law. So Coulomb's law is a quantitative statement, and it was not okay, and it's talking about the forces between 2 point charges. So define பண்ணும்போது we are talking about point charges. When the linear size of the charged bodies are much smaller than the distance separating them, the size may be ignored. So point charges na enadhu? Basically when I am considering them for the calculation of forces, the internuclear distances are such that their sizes can be neglected. So the size may be ignored and the charged bodies are considered to be treated as point charges. So Coulomb measured the force between 2 point charges and found it was varying. It was inversely varying with the square of the distance between the charges and directly proportional to the product of the magnitude of the charges. Okay, fine. So if at all if I have 2 point charges of magnitudes of charges of Q1 and Q2, then the force acting between them is directly proportional to the product of their charges and inversely proportional to the square of the distance between them, and the proportionality constant is K, and let's see what K is. So how did Coulomb arrive at this law? Coulomb used a torsion balance for measuring the force between 2 charged metallic spheres. So basically, what he did was torsion. He used a sensitive device called torsion balance. Yes, in which he was u- he was able to find the force acting between them, and separation between the two spheres is much larger than the radii. The spheres are considered to be point charges. However, the charges on the spheres are unknown to begin with. How then could he discover a relation? Coulomb thought of the following simple way. Suppose the charge on a metallic sphere is q. If the sphere is put in contact with an identical uncharged sphere, the charge will spread over the two spheres. And by symmetry, the charge on each sphere will be q by 2. So hope you are understanding. So basically, if I'm having a particular sphere of particular charge of, let's say, q, and if I have another uncharged sphere of uncharged sphere, and then if I'm bringing together them these particular charges, there will be actually a redistribution occurring, and exactly half the amount of charges will be redistributed on both the spheres simultaneously. Repeating this process, we can get charges of q by 2, q by 4. Coulomb varied the distance for a fixed pair of charges and measured the force for different separation. Now that he has fixed the charges and he measured the separation, he increased or decreased the separations and measured the forces. And then keeping the distance fixed, he didn't he did the other way as well. He fixed the distance and he weighted the charges and compared them, and he gave a quantitative aspect. So Coulomb's law, a simple mathematical statement, was initially experimentally arrived in the described manner, while the original experiments established it at a macroscopic scale. It has also been established down to subatomic level. ஸோ இப்போ ஆக்சுவலாக நம்ம இந்த இப்போ பார்த்த கேசஸ் எல்லாமே வந்துட்டு இட்ஸ் அ மேக்ரோஸ்கோபிக் ஸ்கேல், விச் மீன்ஸ் தட் தேர் கேன் பி மேசிவ் எரர்ஸ் பிகாஸ் வி ஆர் டீலிங் வித் பார்ட்டிகல்ஸ் விச் ஆர் ஆஃப் கம்ப்ளீட்லி தேர் நேக்கட் ஐக்கு பெரிய வாய்ப்பே இல்லாத விஷயங்கள், இமேஜினே பண்ண முடியாத ஒரு லெவலில் இருக்கிற மைக்ரோஸ்கோபிக் பார்ட்டிகல்ஸை வி ஹாவ் டிரைவ்ட் இட் இன் அ மேக்ரோஸ்கோபிக் ஸ்கேல், which means that there could be possibly a lot of errors occurring, but nonetheless they have also established in microscopic level, that is about a 10 power minus 10 meter on the particular level. So Coulomb discovered his law without knowing the explicit magnitude of the charge. In fact, it is the other way around. Coulomb's law can now be employed to furnish a definition for a unit of charge. ஸோ அதாவது ஒரு பர்டிகுலர் சார்ஜோட மேக்னிடியூட் என்ன அப்படின்றது தெரியாமல் கூலும் வந்துட்டு he was able to discover this particular law. Yes, so which means that I can use the other way around. I can define what a unit of charge is. So in the relation k is so far arbitrary, so we can choose any positive value of k. The choice of k determines the size of the unit of charge. So which means that நான் k என்ன வேல்யூ யூஸ் பண்ணுறேன்னா அந்த பேசிஸில் தான் யூனிட் ஆஃப் சார்ஜ் நான் என்னவாக எடுக்க போகிறேன்றத டிட்டர்மினேஷன் ஆக போகுது. In SI units, the value of k is about 9 into 10 power 9. So the unit of charge that results from the choice is called a coulomb, which we defined earlier. So I've taken the arbitrary constant of 9 into 10 power 9 such that the unit of charge that results from in the particular choice la I am obtaining coulomb அப்படின்றதே சொல்கிறாங்க. So which was defined earlier in 1.4. Now if I have a charge of q1 is equal to q2 is equal to 1 coulomb and I have taken the distance to be 1 meter, then the force acting is 9 into 10 power 9 and it turns out to be equal to the k value as well. So that is 1 coulomb is the charge when placed at a distance of 1 meter from another. The charge of same magnitude in vacuum experiences an electric force of repulsion of magnitude 9 into 10 power 9. அதாவது I am redefining coulomb in terms of this particular Coulomb's law. அதாவது என்னென்னா 1 coulomb அப்படின்ற ஒரு பர்டிகுலர் சார்ஜ் என்னதுன்னா it is the amount of it is when placed a meter away from another 1 coulomb charge, the force experienced by the two charges in the particular medium in a vacuum is going to be 9 into 10 power 9 newton அப்படின்ற amount of அப்படின்ற மாதிரி they have defined it. So 1 coulomb is evidently too big a unit to be used. Yes. So in practice in electrostatics, one uses smaller units like 1 millicoulomb, 1 microcoulomb. The constant k in equation 1.1 is usually put as k is equal to 1 by 4 pi epsilon naught for later convenience, so that the Coulomb's law is written in this way. So the magnitude of force acting between 2 point charges of say magnitudes q1 and q2 respectively is 1 by 4 pi epsilon naught times mod of q1 times q2 divided by r square, where epsilon naught is called the permittivity of free space. The value of epsilon naught in SI units is turning out to be 8.854 into 10 power minus 12 coulomb square Newton inverse meter inverse square. So basically it would be better if you know the units as well. It's not gonna take much time. We can do a qualitative analysis, dimensional analysis, but it would be better. I'm not gonna remember actually. Yes, I'm going to just remember the value of epsilon naught permittivity of vacuum, that is 8.85 into 10 power minus 12. So implicit in this is the assumption of additivity of charges and the conservation. அதாவது இந்த பர்டிகுலர் கூலும்ஸ் லாவை பொறுத்த வரைக்கும் வாட் இஸ் கோன் பி இம்ப்ளிசிட் அப்படின்னா, I'm assuming that there is additivity of charges. The particular property of additivity of charges is applicable. Conservation of two charges is applicable. அப்படின்றது தான் இங்கே சொல்ல வந்தாங்க ஆக்சுவலாக. That is the q by 2 factor. Okay. Moving down, since force is a vector, it is better to write Coulomb's law in the vector notation. So yeah, actually I do not have my pencil with me, or else I could easily explain it to you. Yes, so just in case, wait a second. Yes. Okay, let me just give a quick read. Since force is a vector, I'm gonna give it in my vector notation. So let the position vectors of q1 and q2 be r1 bar and r2 bar respectively, and the force on q1 due to q2, I'm just denoting as f1 of 2, that is 1 due to 2, and force on q2 due to q1 is f2 of 1. So the 2 point charges q1 and q2 have been numbered 1 and 2 for the convenience, and the vector r21 is r2 minus r1, and same way r12 is r1 minus r2. The magnitude of the vectors r21 and r12 is denoted by r21 and r12 respectively. The direction of a vector is specified by a unit vector along the vector. To denote the direction from 1 to 2, we define the unit vectors r21 cap is equal to r21 by, okay, that is the vector divided by its magnitude. That will give me the unit vector in that particular direction, and it turns out that the direction of r21 is actually equal to r12. Okay, fine, great. And which means that force on charge 2 due to charge 1 is given by 1 by 4 pi epsilon naught times q1 times q2 by r21 square times r21 cap. So some remarks on the equation 1.3 are relevant. Equation 1.3 is valid for any sign of q1 q2 whether positive or negative. q1 and q2 are same sign, then it's going to be f of 21 is along r21, which denotes repulsion. Okay, wait a minute. So which means that f of 21 is along r of 21 until it's going to be repulsion. As you can see in the particular charges, in the particular figure, first figure, இப்போ ரெண்டு சார்ஜஸோடைய ப்ராடக்ட் if it is turning out to be 0, whether both of them are positive or both of them are negative, then the force on 2 due to 1 it is along the vector r of 2 comma 1, which means that it is actually moving away from the other charge. That is the repulsive type of force அப்படின்ற சொல்கிறாங்க. And similarly, if it is of opposite sign, then it's going to be in the opposite sense, which means that there's an attraction is occurring as expected. The unlike charges are basically getting attracted. So the force F of 1 on 2 on charge q1 due to charge q2 is obtained from equation 2. Okay, fine, great. So basically, if the force acting on 1 due to 2 is negative of the force acting on 2 due to 1, so that's simply interchanging how we're obtaining this, and it is actually agreeing with the Newton's third law as well. The forces are equal and opposite. Yes. So Coulomb's law gives the force between two charges q1 and q2 in vacuum. If the charges are placed in matter or intervening space has matter, the situation gets complicated due to the presence of a charge consequent. So now that we have seen all the things in ideal scenarios only, let's see what will happen if this particular thing is occurring in presence of certain matter in between. But before that, we have certain questions to be answered. So let's try solving them as well. Just a second. So Coulomb's law for electrostatic force between two points such as Newton's law for gravitational force between two points masses have inner square dependence on distance between the charges. So compare the strength of these two forces by determining the ratio of their magnitudes for an electron and a proton and for two protons. Okay, so estimate the accelerations of electron and proton due to the electrical force of their mutual interaction when they are 1 angstrom apart. Okay, basically I will have to have a concordance between Coulomb's law and Newton's law. So let's say I have Coulomb's law. According to Coulomb's law, it's 1 by 4 pi epsilon naught times q1 q2 divided by r square, and side by side I'm writing g m1 m2 by r square. Now comparison ante we'll have to find the ratios. So k q1 q2 by g m1 m2, and first case they have given us they have given, like, we'll have to find for electron and proton. So k's value is 910 power 9, and electron proton both have same charge, but they have an opposite sign, which means that a positive negative multiplied together will obtain a negative thing, and then the charge is going to be 1.6 into 10 power minus 19 whole square. And g oda value, I think it is 6.65 into 10 power minus 34 plus 34. Shit, man, I'm forgetting things. Arre yaar. Wait a minute. Let me just check it once. It's actually 6.675 into 10 power minus 11 into mass of the first guy. Mass of the first guy, the proton, it's actually, oh my god. Mass of an electron is 9.1 into 10 power minus 31 kg, and mass of proton will actually be higher. That's higher about. Hmm, mm, mm, mm. Mass of an electron, mass of a proton. I think it is. Let me just 1 second. Okay, it's a 1.6 into 10 power minus 27. So I'm just calculating the value. It turns out that so electrostatic force is 2.4 into 10 power 39 times that of a gravitational force of attraction between an electron and proton, which is way too higher. Like it can be imagined actually the value. And similarly, if I'm having for a proton-proton interaction, turns out that the particular interaction is gonna be 10 power 36 times. So one of the forces is going to be attractive and the other force is going to be obviously repulsive, as dealing with similar charges and oppositely charged particles in the same time. The electric force F exerted by a proton and an electron is same magnitude to the force exerted by an electron and a proton. However, the mass of an electron and proton difference, thus the magnitude of forces. Okay. Okay, when we are trying to calculate the value of force, it's actually turning out to be 2.3 into 10 power minus 8 newtons. And if I'll have to calculate the acceleration of each particles, then I'll have to divide with each of their respective masses. So for an electron, I will have to divide by 9.1 into 10 power minus 31, and it turns out that it is obtaining an acceleration of 2.5 into 10 power 22. And similarly, for a proton, I'm obtaining an acceleration of 1.4 into 10 power 19 meters per second square. So இதெல்லாம் வந்துட்டு these are certain things like how comparative studies will help us remember things அப்படின்றதுக்கு இது ஒரு எக்ஸாம்பிள். லைக் how far or how great is certain things அப்படின்றது மாதிரி will have a comparative study. So a charged metallic sphere A is suspended to a nylon thread and a charged metallic sphere B held by an insulating handle is brought close to A such that the distance between their centers is 10 centimeter. Okay. So the resulting repulsion of A is noted, for example, by shining a beam of light and measuring deflection of shadow. Spheres A and B are touched by uncharged spheres C and D. Okay. Next case. As shown, and C and D are then removed and B is brought closer to A. Oh. Okay. So what is expected repulsion of A? Spheres A and C and spheres B and D have identical sizes. Ignore the sizes of A and B in comparison to the separation. So it is just that the forces, since the charges have been reduced half of the amount, and the internuclear distance are actually decreased. So charge is becoming half until for each of them that's a 1/4 factor, and I'm actually decreasing the distance that's by a half factor, which means that half square is going to be a fourth, 1/4 on the fourth on the numerator and a by 4 on the denominator, and I don't think there's going to be any change. It remains unaltered. So as they have given, it's going to remain unaltered. Hope you have understood what I did. Yes, and moving down, we'll talk about forces between multiple charges. So basically what happens if I have multiple charges at the same particular point of time. So experimentally it was verified that the force on any charge due to a number of other charges is the vector sum of all the forces on that charge due to the other charges taken one at a time. The individual forces are unaffected due to the presence of the other charges. This is known as the principle of superposition. That is all about this particular topic. So if I have a particle which is surrounded by a few other particles in the same plane, then the particular first particle experiences a force which is a net vector sum of all the forces taken together, vectorally added together, is Coulomb's force on Q1 due to Q3 even though other charge Q2 is present. Thus the total force F1 on Q1 due to the two charges Q2 and Q3 is given as F1 is equal to F of F on 1 on F2 and F of 1 on 3 is equal to 1 by 4 by epsilon Q1 Q2 by R1 2 square by 4 by epsilon Q1 Q3 by R1 3 square. The above calculation of force can be generalized to a system of charges. So basically if I have a system of charges of let's say I have n charges system, and if I'll have to calculate the force on Q1, so which means that force acting on 1 will be the force acting on 1 due to 2, due to 3, due to 4, vectorially adding up. We'll have a k factor common and q factor common and all the other things. That is the summation will occur only for the other charges and divided by their distance from the particular first charge. So the vector sum is obtained as usual by the parallelogram, and yeah, there's nothing to nothing much to do about it. And we have an example over here. Consider the three charges q1, q2, q3 each equal to q at the vertices of an equilateral triangle. What is the force on charge q placed at the centroid of the triangle as shown? Oh my god. So basically I have three charges which has an equal magnitude. I will have to find what is the force on a general charge capital Q which is having the same sign as that of Q. I think it turns out to be 0. Is it so? Sorry, my mistake. Okay, yeah, it is 0 actually. Okay, fine, great. Due to symmetry actually it is 0, but we'll have to give a quantitative aspect. Okay, so basically we'll have to use principle of superposition. So we'll talk about q1q. இப்போ என்ன நடக்க போகுதுன்னா இட்ஸ் the force 1 force on capital Q charge due to q1 is equal to k into capital Q into small q divided by r square. So basically it is an equilateral triangle and this guy is placed at the centroid ante it's actually root 3 by 2l. Yes, so and I think the distance is gonna be, let's take it to be L factor, and moving down we'll have the same expression for every other guys as well. It's kq by L square, kq by L square. Yes, and all these guys are actually separated by an angular distance of 120 degrees with each other, which means since they all have the same magnitude of force that is acting symmetrically at about a point on the three directions, then hence the net force is going to be 0. It is clear also by symmetry that the three forces will sum to 0. Suppose that the resultant force was non-zero but in some direction. Consider what would happen if the system was rotated to 60 degree about O. Okay, so basically if I'm calculating the net force about some direction, not exactly the net force on that particular position, either a particular direction, if I'm trying to calculate the force, then obviously the force in that particular direction be non will not be a zero factor. Will enter the crank time stage. Okay, fine, great. So consider the charges k, okay, q placed at the vertices. What is the force on each charge? Okay, so basically I have to find the amount of force acting on one due to the other two. So basically the two q charges will have same type of force, magnitude of force, and the minus q charge will have a different type, I hope. Basically both will have a type of an attractive force, whereas this q1 and q2 will have a type of a repulsive force. Similarly, okay, sum of the forces under three charges is 0. The result is not at all surprising. It follows straight from the fact that Coulomb's law is considered the proof that is left to you as an exercise. So basically, I will have to use the exercise. Yeah? Fine, great. I'm not into that questions. So let's talk about electric field. So now we are entering into the electric field. So now that we have done with the charges, we'll talk about electric field. Okay, so let us consider a point charge capital Q placed in a vacuum at the origin O. If you place another point charge small q at a point P where OP is equal to R, then the charge capital Q will exert a force on small q as per Coulomb's law. So when we ask the question, if charge Q is removed, then what is left in the surrounding? Is there nothing? If there is nothing at the point B, then how does a force can act when we place charge Q at P? In order to answer such questions, the early scientists, oh my god, yes, in order to answer that questions, so basically the early scientists, what they're trying to do. Introduce the concept of field. According to this, we say that the charge capital Q produces an electric field everywhere in the surrounding, and another charge small q is brought at some point P. The field there acts on it and produces a force. So the electric field produced by the charge capital Q at a point R is actually K capital Q by R square, and the vectors R cap by R is a unit vector from the origin to the point R. Thus, equation 1.6 specifies the value of the electric field for each value of the position vector R. The word field signifies how some distributed quantity, which could be a scalar or a vector, varies its position. Okay. So the effect of the change has been incorporated in the existence of electric field. So we obtain the force if exerted. Okay. Field அப்படின்ற வார்த்தை basically it signifies ஒரு particular distributed quantity which can be scalar or vector varies its position. So the effect of charge can be incorporated. How? Basically we'll multiply the value of charge with the field to obtain the force acting on that particular charge. So know that the charge small q also exerts an equal and opposite force on capital Q. The electrostatic force between the can be looked upon as an interaction between charge small q and electric field of capital Q and vice versa. We denote the position of charge small q by the vector R. It experiences a force F equal to the charge small q multiplied by the electric field E. So quantitatively, the force acting on that particular small q charge due to this particular field present by the capital Q is going to be equal to the magnitude of small q charge multiplied by the field. So basically, the equation 1.8 defines the SI unit of electric field as Newton per Coulomb. Yes, obviously. Some important remarks. We can infer from Q is that NIT that the electric field due to the charge Q, capital Q is numerically equal to the force exerted by this. The electric field due to a charge capital Q at a point in a space may be defined as the force that a unit positive charge would experience if placed at that point. Okay. So quantitatively, how am I defining it? The force experienced by the unit positive charge due to the presence of a charge capital Q. So the charge capital Q which is producing the electric field is called a source charge, and source charge small q which tests the effect of a source charge is called a test charge. Okay, fine. The source charge capital Q must remain at its origin location. However, if the charge small q is brought at any point around capital Q itself is bound to experience an electrical force due to small q and we will tend to move. A way out of this difficulty is to make q negligibly small. So the force capital F is then negligibly small, but the ratio of F by Q is finite and defines the electric field. Okay. Right. Fine, great. So practical way to get around the problem is to hold capital Q's location by unspecified forces. This may look strange, but actually this is what happens in practice. When we are considering the electric force on a test charge small q due to the charged planar sheet, the charges on the sheet are held to their locations by the forces due to the unspecified charged constituents inside the sheet. Okay. When we are considering electric force on a test charge small q due to a charged planar sheet, okay, note that the electric field E due to Q, though defined operationally in terms of some test charge small q, is independent of Q. spherical symmetry. So basically, electric field, it does not depend upon the test charge that we are using, but it is dependent upon the what's the particular charge that is producing the field, and it depends upon the coordinates of distance on which at which the field is being determined. If a positive charge is going to be directed radially outwards, and for a negative charge it's going to be directed radially inwards. And the magnetic force, it depends upon the distance, and the magnitude of field E will also depend on that. So which means that for equal distance from charge P, the magnitude of its electric field is going to be the same. Okay, so when we are talking about electric field due to a system, as we have seen in force, the same is going to be applicable. Since it's a vector quantity, we can make use of the superposition principle, and we can just add up the things vectorially since it's a vector as well. And we'll talk about the physical significance, which I feel is important to be known. That is, you may wonder why the notion of an electric field has been introduced here at all. After all, for any system of charges, the measurable quantity is the force on a charge, which can be directly determined by the Coulomb's law and superposition principle. Why then introduce this intermediate quantity? So basically, எந்த ஒரு particular system எடுத்துக்கிட்டிங்கனாலும் force அப்படின்றது it is easily calculatable. ஏன் அப்படின்னா it's actually it can be perceived in our day-to-day lives. It can be calculated using this particular law of Coulomb's, and we can use the superposition principle as well. So for electrostatics, the electric field is convenient but not really necessary. So it will be convenient factor but not a necessary factor. So electric field is an elegant way of characterizing the electrical environment of a system of charges. Electric field at a point in the space around the system of charges tells you the force a unit positive test charge would experience if placed at that particular point. So electric field is a characteristic of the system of charges and is independent of the test charge that you place at the point. அதாவது let's say have a system of charges. இப்போ அந்த பர்டிகுலர் இடத்துல if I'm placing a test charge, nonetheless if I'm placing or not, or if I'm placing a test charge of say 1 magnitude q1, and if I'm placing another test charge of q2, according to the presence of the charges, the forces are going to obviously vary, which means that there's something related generally, that is we are trying to generalize certain things, and accordingly for each and every given test charge we'll calculate the amount of force happening on it, which means that the very generalizing factor that is happening at this particular point is what is where we are making use of this concept of electric field, which is actually independent of the test charge that we are trying to find the force of. அந்த பர்டிகுலர் சார்ஜில் எவ்வளோ ஃபோர்ஸ் ஆக்ட் ஆகும் அப்படின்றது தெரிஞ்சுக்கிறதுக்கு வந்துட்டு we do not need the charges value if we know the electric field அப்படின்றதான் சொல்லுவாங்க. So the term field in physics actually it refers to the quantity that is defined at every point in space and may vary from point to point. So field அப்படின்றது என்னது, it is basically defined at every point and it can vary point to point. Electric field is a vector field since force is a vector quantity. The true physical significance is, however, emerges only when we go beyond electrostatics and deal with time-dependent electromagnetic phenomena. Electrostatics it is not of much use, but when we are talking about time-dependent electromagnetic phenomena. Suppose we consider the force between the two distant charges q1 and q2 in accelerated motions, which means that the greatest speed with which a signal or information can go from one point to another is c. Thus, the effect of any motion of q1 on q2 cannot arise instantaneously. There will be some time delay between the effect force on q2 and the cause motion of q1. So it is precisely here that the notion of electric field is natural and very useful. The field picture is that the accelerated motion of charge q1 produces electromagnetic waves, which then propagate with the speed of c, reaches q2 and causes a force on q2. So basically என்ன சொல்கிறாங்கன்னா electromagnetic phenomena ஒன்றும் இல்லை. Basically if I have an accelerated motion of charges, obviously there will be electric forces due to the particular charge, and then due to acceleration of motion, charges will have magnetic phenomena as well. இப்போ suppose that the acceleration of q1 obviously produces both electric and magnetic field, which means that for reaching out this force, in the particular force wanted, for reaching it out towards q2, it will require some time, it will have some time delay. And for இந்த பர்டிகுலர் ஃபேக்டரை வந்துட்டு எக்ஸ்பிளைன் பண்ணுறதுக்காக the theory proposed of electric field is much useful. So it is such that basically the accelerated motion of charge q1 produces electromagnetic waves, which then propagate at the speed of c, and it reaches q2 and causes a force. So the notion of field elegantly accounts for the time delay. So time delay அப்படின்ற ஃபேக்டரை வந்துட்டு அக்கௌண்ட் பண்ணுறதுக்காக we are making use of this very notion of electric field. Not only electric field, any type of field that we will be covering in the upcoming chapters. So they are regarded as physical entities. Okay. Thus, even though electric and magnetic fields cannot be detected only by their effects on charges, that is the forces, they are regarded as physical entity, not merely for mathematical constructs. They have an independent dynamics of their own. That is, they evolve according to the laws of their own. So they can also transport energy. There's a source of time-dependent electromagnetic fields turned on briefly and switched off leaves behind propagating electromagnetic fields transporting energy. The concept of electric field was first introduced by Faraday and is now among the central concepts in physics. So ஏன் அப்படி இந்த physically how I am defining, why am I defining அப்படின்றத பார்த்தோம். Now we will have certain questions to be answered. Just a second. Okay, so we have questions over here. Yes, so let's see what's happening. An electron falls through a distance of 1.5 centimeter in a uniform electric field. Okay, so the direction of the field is reversed, keeping its magnetic unchanged, and a proton falls to the same distance. Compute the time of fall in each case. Contrast the situation with that of free fall under gravity. Oh my god. So basically, first case மட்டும் பார்ப்போம். Field is upwards. இப்போ electrons will move in the opposite direction because, okay, fine. So the negative charge experiences downward force where capital E is the magnitude of the electric field, the acceleration of the electron. Okay. The acceleration of electron is basically the magnitude of charge multiplied by the magnitude of electric field divided by mass of electron. And when we are starting from the rest, the time required by the electron to fall through a distance h is given by root 2h by whatever the acceleration that the electron is experiencing. That is, it is experiencing an acceleration of 2h me by e for small e is equal to 1.6 into 10 power minus 19 coulomb. Mass of electron is 9.1 into. Okay, fine, great. So which means that the time e is turning out to be 2.9 into 10 power minus 9 seconds. The field is downward and the positively charged proton experiences a downward force of magnitude small e into capital E. The acceleration of the proton is, okay, so where mp is the mass of the proton, mp is 1.67 into 10 power minus 27 kilogram. The time of fall for the proton is 1.3 into 10 power minus 7 seconds. Okay, so for electron it is relatively easier, it's 10 power minus second as it is falling downwards. Okay, and for proton it's turning out to be a bit more. So thus the heavier particle takes a greater time to fall. This is in basic contrast to the situation of free fall, where the time of fall is independent of the mass of the body. Note that in this example we have ignored the acceleration due to gravity in calculating the time of fall. So to see if this is justified, let us calculate the acceleration proton in the given electric field. Okay. So as you can see, the acceleration proton in the given electric field is turning out to be 1.9 into 10 power 12 seconds, which is actually far greater than the value of gravitational field. So the acceleration of gravity is not taken into much consideration. So and it can be ignored. Okay. So 2 point charges Q1, Q2 magnitude of 10 power minus 8 coulomb and 10 power minus 10 power minus 8 coulomb. Okay, place one. Fields at points A, B, and C. Okay, where is C? It's there. B is over there. Where is C? Okay. So for calculation of field, I will have to make use of the principle of superposition. And I'll have to add them vectorially, which I'm not interested in doing now. Let's try doing questions in the book back after some time. Now we'll talk about the electric field lines. We have studied electric field lines. Okay, electric field is a vector quantity represented by vectors. Now we'll try representing the electric field due to a point charge vector. Let the point charge be placed at the origin and draw vectors pointing along the direction of the electric field, okay, with their lengths proportional to the strength of the field at each point. Okay, so as you can see, higher the strength, longer is the line, and the longer lines are actually closer to the particular charge that we have. So basically we are taking care, we are having a positive charge, positive point charge. So that's why the electric field is moving away from the positive point charge, as you can see. It is pointing radially outward. Each arrow indicates electric field. The force acting on a unit positive charge placed at the tail of the arrow. Connect the arrows pointing in one direction, and the resulting figure represents a field line. So a particular direction arrows connect it is actually pointing towards it, representing a field line. We thus get many field lines all pointing outwards from the point charge. Have we lost the information about the strength? No. Now the magnitude of the field is represented by the density of field lines. So magnitude of electric field is strong near the charge, so the density of field lines is more near the charge and the lines are closer. Away from the charge, the field gets weaker and the density of field lines is less, resulting in well separated lines. So basically the amount or the strength of the field is actually represented by the amount of field lines present in a given area or crossing a given amount of area, that is the density. So higher is the density, more is the field, electric field in that particular position. So another person may draw more lines, but the number of lines is not important. In fact, an infinite number of lines can be drawn in any region. Okay, so it is the relative density of lines. So as you can see, there is a point charge q. So at nearer to the charge, the density is much higher, and as we go far away, the basic electric field strength is actually decreasing. Yes. So we draw the figure, okay, in 2 dimensions, but we live in 3 dimensions. So if one wishes to estimate the density of field lines, one has to consider the number of lines per unit cross-sectional area. So since electric field decreases as the square of the distance from a point charge and the area enclosing the charge increases as the square of the distance, the number of field lines crossing the enclosed area remains constant. Okay, whatever may be the distance of the area from the charge. So we started by saying that the field lines carry information about the direction of electric field at different points. Having drawn a certain set of field lines, the relative density of the field lines at a different points indicates the relative strength of the electric field. The field line crowd where the field is strong and are spaced where it is weak. Okay, fine, great. Understand the dependence of the field lines on the area, or rather the solid angle subtended by an area element. Let us try to relate the area with a solid angle, a generalization of an angle to 3 dimensions. Similarly, solid angle is actually defined as the perpendicular plane area divided by the inverse square of distance, and know that in a given solid angle the number of radial field lines is the same. So 2 points P1 and P2 at distances R1 and R2 from the charge. The element of area subtending the solid angle is R1 square into solid angle. Okay, great. Okay, so the number of lines cutting the area elements are the same. The number of field lines cutting unit area element is there. So since Mn field is clearly has a dependence on 1 by r square, the picture of field lines has invented an intuitive non-mathematical way of visualizing electric fields. The lines of force. This term is somewhat misleading, especially in case of magnetic fields. The more appropriate term is field lines that we have adopted this. Okay. Electric field lines are thus a way of pictorially mapping the electric field around a particular surface. Electric field line is in general a curve drawn in such a way that the tangent to at each point is in the direction of the net field at that point. An arrow on the curve is obviously necessary to specify the direction of the direction of electric field from the two possible directions indicated by tangent to curve. A field line is a space curve, that is a curve in 3 dimensions. Okay. Figure 1.7, as you can see, for basically a field line is a curve drawn in such a way that the tangent to it at each point gives me the direction of net field. And yeah, field line is in a space curve, that is a curve in 3 dimensions. Okay. Q greater than 0, Q less than 0. Okay, fine, great. Now we'll say certain properties. They start from positive charge and at negative charge in a charge-free region. Electric field lines can be taken to be continuous curves without any breaks. Two field lines can never intersect each other or cross each other. As if we do that, then there will not be a unique direction. Electric field lines can be taken to be continuous curves without any break. Okay, and electrostatic field lines do not form any closed loops. So why, we'll see it in the next chapter. Okay, now we'll enter into the topic of electric flux. So basically we'll consider the flow of a liquid with a velocity v through a small flat surface ds in a direction normal to the surface. The rate of flow of liquid is given by the volume crossing the area per unit volume. Every time, that is v ds, and represents the flux of liquid flowing across the plane. So if the normal to the surface is not parallel to the direction of flow of liquid, that is to v, but makes an angle theta with it, the projected area in a plane perpendicular to v is v ds cos theta. Therefore, the flux going out of the surface ds is v dot n cap ds. Okay, so in the case of electric field, we define an analogous quantity called electric flux. flux of liquid அப்படின்றது the volume of liquid, that is the rate of flow of liquid, that is it is the total amount of volume crossing an unit area per unit time அப்படின்றது. And if it is not parallel, then we'll make use of a cos theta component. We'll only take care of all the cos theta components, and the flux going out of that particular surface for that particular liquid flow is basically v dot n cap multiplied by the area of cross section. So now that we'll have an electric field in which a similar electric field line can be considered for to be flowing, then we can have an analogous quantity called an electric flux. So we should, however, note that there is no flow of physically observable quantity, but this actually something mathematical aspect of how forces are acting. So in the picture of electric field lines described, we saw that the number of field lines crossing a unit area placed normal to the field at a point is a measure of the strength of electric field at that point. So அதை என்ன சொல்ல வராங்கன்னா, the picture of electric field lines described, we saw that the number of field lines crossing a unit area placed on. Okay, so this means that if we place a smaller planar element of area delta S normal to E at a point, the number of field lines crossing it. Okay, fine, great. Now suppose we tell the area element by theta angle, as the number of field lines crossing delta is proportional to E delta S cos theta. The theta is equal to 90 field lines will be parallel. Okay, great. As you can see, if it is a parallel guy, then basically it is actually E delta S, but if it is tilted by an angle theta, then we will consider only a cos theta component. Okay, so the orientation of area element and not merely its magnitude is important. So for example, in a stream, the amount of water flowing through a ring will naturally depend on how you hold the ring. If we hold it normal, the maximum water flow will obtain. And okay, fine. An area element should be treated as a vector. It has a magnitude and also direction. How to specify direction? Clearly normal to the plane specifies the orientation of the plane. Thus the direction of planar vector is along its normal. How to associate a vector to the area of a curved surface? We imagine dividing the surface area into a large number of very small area elements. Each small area element may be treated as a planar or the vector associated with it. Notice one ambiguity here. The direction of an area element is along its normal, but a normal can point in two directions. Which direction do we choose as the direction of vector associated with an area element? So basically that we'll have two normals. Let's say if I'm considering a plane surface, then which one will I consider to be the normal? So it is resolved by some convention appropriate to the context. For the case of a closed surface, this convention is very simple. So the vector associated with every element area of a closed surface is taken to be in the direction of the outward normal. In case of a closed surface, we will talk only about the outward normal. This is the convention used in figure 1.19, as you can see. So this is okay. So we now come to the definition of electric flux. The electric flux delta phi through an element delta S is defined by E dot delta S, that is E delta S cos theta, which as seen before is proportional to the number of field lines cutting the area element. The angle theta here is the angle between E and delta S for a closed surface. With the convention stated already, theta is the angle between the electric field and the outward normal to the area element for a closed surface. Notice we could look at the expression E delta S cos theta in two ways. E into delta S cos theta, that is E times the projection of area normal to the electric field, or the perpendicular value, that is the component of electric field along the normal to the area element times the value of the area, magnitude of area, gives me electric flux. It can be taken in both ways. The basic definition of electric flux given by equation 1.11 can be used in principle to calculate the total flux through any given surface. All we have to do is to divide the surface into small area elements, calculate the flux at each element, and then add them. Thus the total flux is actually summation of E dot delta S. So what we have seen in equation 1.1 is for the calculation of flux in a differential amount of area, and in that particular differential area it's going to be E dot delta S. Okay. The approximation sign is put because the electric field E is taken to be constant over the small area element. This is mathematically exact only when you take the limit delta S tends to 0 and the sum in equation 1.12 is written as an integral. Electric dipole. An electric dipole is a pair of equal and opposite point charges q and minus q, okay, separated by distance 2 alpha. The line connecting the two charges defines a direction in space. By convention, the direction from minus q to plus q is said to be the direction of the dipole. So now we are entering into the concept of dipole, in which we have 2 point charges plus q and minus q. Yes, and it is separated by distance 2a. Why we have taken the 2a, we will see by convention. The direction will be taken from minus q to plus q. So that will be the direction of the dipole. The midpoint of the locations of minus q and plus q is called the center of the dipole. Okay, the total charge of the electric dipole is obviously 0. This does not mean that the field of the electric dipole is 0. Okay, so since the charge q and minus q are separated by some distance, the electric fields due to them when added do not exactly cancel out. However, at distances much larger than the separation of the two charges forming a dipole, the field due to plus q and minus q nearly cancel out. Okay, the electric field due to a dipole therefore falls off at large distance faster than like 1 by r square on r of the field. Okay, on distance r of the field due to a single charge. These quantitative ideas are born out of explicit calculations. Okay, so what they're trying to say is that we'll have a concept of electric dipole in which we'll have equal and opposite charges of equal magnitude with opposite polarities placed by, separated by a fixed distance of 2a, and that the direction will be taken from the direction from minus q to plus q. Okay, so this does not mean that the field of the electric dipole is 0. Okay, fine, great. Electric field due to them when added do not exactly cancel out. Okay, however, distance is larger than the separation between them from the dipole. The fields due to q and minus q nearly cancel out. Okay, fine, great. We will see the field of an electric dipole. Okay, so actually in this particular book, that's the thing actually I wanted to say. நம்மளோட பழைய புக்கை பொறுத்த வரைக்கும், அதாவது 2018-19 versionல we have certain derivations, whereas in our new book we do not have. So that's why I'm making use of this particular book, the old book. So on a plane perpendicular to the dipole axis through its center, the electric field at any general point P is obtained by adding the electric fields due to charge minus q plus q and by the electroparallelogram law of vectors. So what I'm gonna do is that try finding the value of electric fields due to both the charges when the point is on the dipole axis and when it is on the equatorial plane of the dipole, that is on a plane perpendicular to the dipole. Okay, we'll calculate it in two aspects. Now we'll try finding the value for the points on an axis. So it would be better if you just write side by side what's actually happening. So what we are going to do is find the electric field due to a dipole on axis. So basically value of electric field is going to be q plus is going to be 1 by 4 pi epsilon naught times that's field, so which means that it's due to a plus charge. It's 1 plus 1 by 4 pi epsilon times cubed by r plus a the whole square. Why is it so? Let's say it is okay, this particular distance is a and this particular distance is a. This is plus q and that's a minus q factor. In figure 1.20 எங்கம்மா அது அந்த இருக்கு. Will always take the distance from the center of the dipole. That's why I have to calculate the value of distance r from the center of the dipole. And since the guy q is at a distance plus a, so I'm just adding it by, minus a. I'm sorry, it's a minus a factor. According to our convention, I'm taking it to minus a. Okay, fine. Similarly, q minus is going to be equal to minus 1 by 4 pi epsilon r times q by r plus a the whole square. So these are the two values of electric field. Now we'll talk about the total field. So total field will be the vectorial sum of these two guys, and since they are lying on the same line, so I will not care about that angles or theta or whatever. We'll take one side to be positive, and consequently the one acting on the other side will be taken negative. So the electric field, net electric field is actually E plus Q plus E minus Q. That's q by 4 pi epsilon naught will be taken as a common, and it's a 1 by r minus a the whole square minus 1 by r plus a the whole square p cap. Yes, I don't think it's actually difficult. Hope we are able to understand it. Yes, so since we take the direction of dipole to be from negative towards the positive end, so from the negative end, அதாவது towards the left, I'm taking it as positive. Yes, which means that consequently the other guy will be taken negative, and that's why the minus q factor is taken to be a negative according to my convention and whatever the convention is being followed in NCERT. So which means that it's a q by 4 pi epsilon naught times 4ar by r square minus a square the whole square. Speak up. Now that if value of the internuclear distances is far lesser than the distance through which I'm calculating the value of electric field, then in such case scenarios, I will basically approximate A to be nullified in front of R square factor, and an R in the numerator and an R power 4 factor in the denominator cancels out to give me a final value of Q. 4qa by 4 pi epsilon naught times R cube P cap. That is in the direction P cap in the direction is taken from the negative towards the positive. Yes. தூக்கி கொண்டு போறேன்டா ஞாபகத்துக்குள்ள அடிக்கிற மின்னலு நீதான் காரணம் என் மனசுக்குள்ள. Just a second. Okay, and similarly we'll calculate the value of electric field on the equatorial planes as well. So let's say the value will first of all consider an equatorial plane. Okay, so let's say I have a plus q and a minus q, both separated by a distance of 2a, and I'm having an equatorial plane exactly in the midway. I'm considering an equatorial plane exactly in the midway, which is perpendicular to the dipole. Yes, that's the direction of the dipole, and let's say I'm having a point P on this particular equatorial plane, which is subtending an angle theta. Obviously it is at an equal position, it means that it will have an equatorial plane, equal angle being subtended by both both the ends. So there will be an electric field due to the plus q charge, and an electric field will be towards the minus q charge, and there will be a net electric field acting at that particular point P. Yes, hope it is fine till now. Now that we have the values, let's try calculating. So E plus Q is a cube by 4 pi epsilon naught times 1 by r square plus a square. Why is it so? So basically the r is the particular distance from the center, and it is at a value, and similar will be the case in minus q as well. It's a minus q by 4 pi epsilon naught times 1 by r square plus a square. Yes, so we'll have to find the net electric field acting, and the net electric field acting is in the opposite direction. As you can see, it's in the opposite direction of the actual value of electric dipole. So I am taking a negative sign to make a nullifying effect. So E plus Q plus E minus Q times cos theta. Only the cos theta components are considered at this particular moment. Okay, hope you understand why we are considering the sin theta components are basically not along that particular value. That is, they get cancelled out, they get nullified. So we are considering the cos theta components, and then yeah, there you go. Finally, I am obtaining a minus 2qa by 4 pi epsilon naught times r square plus a square the whole power 3 by 2 p cap. So basically for cos theta, I've considered the adjacent by hypotenuse value, and that's why it turns out that I'm having a by r square plus a square factor into consideration. Okay, fine. And if I have the distances larger than r, okay, so in such case scenarios, I can basically the r I mean a square factor will be considered too small in front of r square, which means that I will have a minus 2qa by 4 pi epsilon naught times r cube. Yeah. So as you can see, the equatorial value of, equatorial plane, the value of electric field is turning out to be opposite to that of the direction of electric dipole. And in case of an axial field, it's going to be in the direction of the electric dipole. Now it seems like a very long factor, so it's clear that the dipole field at a large distances does not involve the q and a. It depends on the product qa. ஸோ அதாவது லார்ஜ் டிஸ்டன்சஸில் பார்க்கும் பொழுது QA அப்படின்னு இண்டிபெண்ட் டிபெண்டன்ஸ் இல்லாமல் இட் இஸ் பேசிக்கலி ஹேவிங் அ மல்டிப்ளிகேஷன், தட் இஸ் Q into A, so which suggests the definition of dipole moment. So dipole moment is defined as the magnitude of charge multiplied by the internuclear distances, whatever the distances. It's a vector whose magnitude is charge, so Q times the separation to A, and the direction is along the line from minus Q to plus Q. In terms of P, the electric field of a dipole at large distances takes simple forms. So basically at a point on the dipole axis, the electric field E is turning out to be 2P by 4 pi epsilon naught times R cube. And at a point on equatorial plane, it is minus P by 4 pi epsilon naught times R cube. And if I consider it as in terms of K, it's actually 2Kp by R cube, 2kp by r cube for electric field in axial position, and it's going to be minus kp by r cube in case of an equatorial, if I'm calculating a point, considering a point at an equatorial plane. Okay, so notice that point that the dipole field at a larger distances falls off not as 1 by r square, but it is falling as 1 by r cube factor. So the magnitude and the direction of dipole field depends on not only on the distance r, but also on the angle between the position vector r and the dipole moment p as well. So as you can finally see a quantitative aspect of what the dipole moment is, you can generally, you can control certain factors, like it depends upon the 1 by r cube factor, it depends upon the angle between the position vector and the dipole moment. Yes. Now moving on. So you can think of the limit when the dipole size 2a approaches 0, the charge small q approaches infinity in such a way that the product of dipole moment turns out to be q multiplied by 2a is finite. Such a dipole is referred as a point dipole, and for point dipole, equations 1.2 and 1.21 are exactly true. Okay, as you can see, the value for a point dipole na basically the internuclear distances are considered to be much smaller than the distance at which you are calculating the electric field. In such case scenarios, these two values are actually considered good or can be useful. So the physical significance, in most molecules, the centers of positive charges and the negative charges lie at the same place, which means that there will be a net dipole moment, but the dipole moment is turning out to be 0. In carbon dioxide, methane are this type of molecules. However, they develop a dipole moment when an electric field is applied. But in some molecules, the centers of negative charge and positive charge do not coincide. Therefore, they have a permanent electric dipole moment, even in the absence of an electric field. Such molecules are called polar molecules, like water, which is an example. Various materials give rise to the interesting properties and important applications in the presence or absence of an electric field. Okay, we have been given with certain questions over here. So two charges plus minus 10 microcoulomb are placed 5 mm apart. Determine the electric field at A, a point P on the axis of the dipole 15 cm away from the center. Okay. Abhi Saleh. Actually, I'm feeling tired. Let me just have a break for now. Gauss's law is true for any closed surface, no matter what its shape or size is. Yes. And the term small q on the right side of Gauss's law includes the sum of all charges enclosed by the surface. It may be located anywhere inside the surface only. In the situation when the surface is so chosen that there are some charges inside and some charges outside, the electric field on the left side, that is whose afflux, okay, is due to all the charges both inside and outside. Yes. Okay. The term small q on the right side of the Gauss's law, however, represents only the total charge inside us. அதாவது என்ன சொல்ல வராங்கன்னா, இந்த எலக்ட்ரிக் ஃபீல்டு வந்துட்டு இப்போ if I'm considering a surface, yes, such that there are certain charges that is coming inside and certain charges coming outside. லெஃப்ட் ஹேண்ட் சைடில் இருக்கிற அந்த பர்டிகுலர் E dot dsல the electric field will be considered for the presence of both the charges, whereas in case of on the right hand side we'll have only the term that is we'll have the terms that is present inside the surface. Okay, that's something important that we'll have to note down. The surface that we choose for the application of Gauss's law is called the Gaussian surface. So basically surface is not good, so they've termed it as Gaussian surface. Now you may choose any Gaussian surface and apply Gauss's law. However, take care not to let the Gaussian surface pass through any discrete charge. Okay, which means that this is because the electric field due to a system of discrete charges is not well defined at the location of any charge. Okay. Gaussian surface it should not pass through any discrete charge. Okay, which means that as you go close to the charge, the field grows. However, the Gaussian surface can pass through a continuous charge distribution. Otherwise, we'll have to make sure that it does not pass through a discrete charge system, but it passes through a continuous charge distribution. Gauss's law is often useful towards a much easier calculation of the electrostatic field when the system has some symmetry. Okay. Useful towards a much easier calculation of the electrostatic field when the system has some symmetry. Ooh. Okay. So this is facilitated by the choice of the suitable Gaussian surface, and Gauss's law is based on the inverse square dependence. So any violation of Gauss's law will indicate departure from the inverse square law. So வந்துட்டு சில முக்கியமான aspects of Gauss's law is that it is true for any closed surface, and the charge enclosed must be inside the charge, and the charge chosen will always be inside the charge, and for calculation purposes the electric field though will be considered for all the charges that is present in the proximity of that particular surface. Will have only the charges enclosed in the right hand side of the Gauss's law equation, and the surface has to be chosen in such a way that it has certain symmetry, and it follows and it is passing through a continuous charge distribution and not has certain discrete charges. And Gauss's law is based on the inverse square dependence on the distances contained. Okay, so moving on, electric field components. Okay. Electric field components. Oh my god. Damn. Fine, great. What I will have to calculate is the flux through the cube and the charge within the cube. Fine, great. What they have given. There is a net electric field in the positive x direction. Yes, it grows. Okay. Has a proportionality constant of alpha, which is about 800. I have to find the flux through the cube and the charge within the cube. So flux is basically given by E dot delta S. So net flux through the cube will be calculated by the net area through which it is passing through. So since it's not, the perpendicular components are not considered, we'll calculate only for the left surface and the right surface. So the electric field passing through, the flux passing through the first surface, the left surface, is calculated by Ex dot delta S, and since the normal to the out surface is negative, so which means that I will take a negative sign in advance, and we'll have the alpha x power 1 by 2 multiplied by the value of the area is turning out to be a square, and a is turning out to be 0.1. 0.1 square is 10 power minus 2, so it's a minus 10 power minus 2 multiplied by alpha. Alpha is actually 800 multiplied by x. Okay, shit man, arrays. Okay, I think at the left surface we have x to be equal to a. Yeah, they have they have denoted it, so which means x is considered to be a power 1 by 2, and a is actually minus 10 power 2 minus 10 power minus of 10 power minus 2 into 800 into 0.1, that is 10 power minus 1 by 2. So that is the flux through the left surface, and the flux through the right surface is actually calculated as Ex dot delta S. That's since both the area vector and the electric field vector are on the same direction, so I will have a positive sign. So that's alpha x power 1 by 2 multiplied by area. Area is going to be a square, and x is turning out to be alpha times x plus x, that is a plus a, that's a 2a factor, 2a power 1 by 2 times a square. So that's a root 2 alpha a power 3 by 2. Yes, 2 plus 1 by 2 is 5 by 2 actually. I'm sorry, my mistake. And root 2 times 800 plus into a is 0.1. That's a 10 power minus 5 by 2. So finally adding these guys too, and then I will obtain the net flux. It turns out to be 1.05. Now that the net flux is turning out to be 1.05, that multiplied by the epsilon naught gives me the net charge enclosed. Now the net charge enclosed in that particular surface is 1.05 into 8.85 into 10 power minus 12 coulombs, and that turns out to be somewhere around 9.27 into 10 power minus 7 minus 12 coulombs. Yes. So moving down, we have another question. An electric field is uniform and in the positive x direction for positive x, and in uniform with the same magnitude, but in the negative x direction for negative x. Electric field is uniform and in the positive x direction for positive x. That x positive or the direction is also in the positive direction, and it is uniform with x same magnitude, ஆனால் it is in the opposite direction for negative x அப்படின்னு சொல்கிறாங்க. Okay, fine, great. And it is on the positive and negative x direction, right? Okay, it is given that the value of electric field is 200 for x greater than 0, and okay, fine. A right circular cylinder of length 20 cm, radius 5 cm, has its center at the origin and its axis along the x-axis. Excellent. So what I am having is this scenario. Basically there's an electric field with its center exactly coinciding with the origin, which means that one half will have an electric field that will be on the right hand side, and the other half will have an electric field that is in the left hand side. So what I will have to find is the net outward flux through each flat face, and what is the flux through the side of the cylinder. So side of the cylinder, since it is perpendicular, it's obviously going to be 0. And what is the net outward flux through the cylinder? Net outward flux is going to be the sum of left flux plus the right flux. And what is the net charge? That left flux plus right flux multiplied by epsilon naught they will give me. So அதுக்கு முதல்ல லெஃப்ட் ஃப்ளக்ஸும் ரைட் ஃப்ளக்ஸும் கால்குலேட் பண்ணுவோம். 5L is equal to electric field in the left hand side multiplied by the value of the area vector. Area vector, it turns out to be in the direction of electric field, which means that it is ஆலியிலிருந்து அலசி திறந்தேனே அடைக்கலம் அழிக்க தகுந்து வந்தாயே அடியலகா சிரிச்ச முகமே நான் நினைச்சா தோணுமே. Radius turns out to be 0.05 centimeter, and the flux will be positive since both of them are in the same direction. So it's a 200 multiplied by 5 into 5 centimeter in meters is 0.05 the whole square. So we'll try calculating it. So 5 square is a 25 factor, and a 10 power minus 2 it's a 10 power minus 4 factor. 10 power minus 4 into 10 power 2 is a 10 power minus 2 factor. That multiplied by 2 into pi will give me a 50 pi into 10 power minus 2 is the flux on the left side. And similarly we have on the same value will be on the right hand side as well. There will be a 50 pi into 10 power minus 2, and the net flux flowing will be 100 pi into 10 power minus 2. And if I'll have to calculate the net charge enclosed, that multiplied by epsilon naught, that's a 8.85 into 10 power minus 12. Yes. Okay. Now that we have seen what are the parts of Gauss's law, now we'll make use of this Gauss's law to obtain that basically the applications. The electric field due to a general charge distribution as seen above given by equation 1.27. In practice, except for some special cases, the summation involved in this equation cannot be carried out to give electric field at every point in space. ஓகே ஒரு நிமிஷம் இருங்க. சில ஸ்பெஷல் கேசஸை தவிர அந்த இன்டிகிரேஷன் இன்வால்வ்டு வந்துட்டு இட் கேனாட் பி கேரிட் அவுட் டு கிவ் எலக்ட்ரிக் ஃபீல்ட் அட் எவ்ரி பாயிண்ட். ஸோ ஃபார் சம் சிமெட்ரிக் சார்ஜ் configurations it is possible to obtain the electric field. So if at all if I have a symmetric charge configuration, then yeah, it will be easier to calculate. So let's see the field due to an infinitely long straight uniformly charged wire. So NCERT பொறுத்த வரைக்கும் we will calculate only for a wire, a plane sheet and then for a thin spherical shell. அவ்வளோதான். Yes, so we'll move on. So consider an infinitely long thin straight wire with uniform linear charge density lambda. The wire is obviously an axis of symmetry. Suppose we take the radial vector from O to P and rotate it around the wire. The points P, P dash, P double dash so obtained are completely equivalent with respect to the charged wire. So basically it's actually considered with the wire at the center of this particular spherical, as a circular surface. Yes. So this implies that the electric field must have the same magnitude at these points. Okay. The direction of electric field at every point must be radial. Right. So this is clear from figure 1.29. So என்னென்னலாம் இப்போ கன்க்ளூட் பண்ணியிருக்கோம், இந்த சுற்றி இருக்கிற பி டேஷு பி டபுள் டேஷ் எல்லாமே ஒரே டிஸ்டன்ஸில் இருக்கான். அவன் எல்லா இடத்துலையுமே வந்துட்டு டிரெக்ஷன் ஆஃப் எலக்ட்ரிக் ஃபீல்டு வந்துட்டு இட் வில் பி ரேடியல் அண்ட் அதே சமயத்தில் ஈக்குவல் டிஸ்டன்சஸில் வந்துட்டு த எலக்ட்ரிக் ஃபீல்டோட வேல்யூ வில் பி ஈக்குவல். கன்சிடர் பேர் ஆஃப் லைன் எலிமெண்ட்ஸ் P1 and P2 of the wire. The electric fields produced by the two elements of the pair when summed give a resultant electric field which is radial. So basically I am having a pair of line elements P1 and P2 it seems. Okay, fine. What they're trying to say over here, the electric fields produced by the two elements of the pair and summed give a resultant electric field which is radial. The components normal will be cancelled and the radial components will only be the net electric field. This is true for any such pair and hence the total field at any point is radial. Finally, since the wire is infinite, electric field does not depend on the position of the P along the length of the wire. In short, the electric field is everywhere radial in the plane cutting the wire normally. Wire வந்து இன்ஃபைனைட்டாக இருக்குது and it does not depend on the position of P, which means that basically electric field is everywhere radial in the plane and cutting the wire normally and its magnitude depends only on the radial distance. So to calculate the field, imagine a cylindrical Gaussian surface. ஸோ இப்போ நம்ம என்னென்னலாம் கண்டுபிடிச்சிருக்கோம் அப்படின்னா, பேசிக்கலி ஈக்குவல் டிஸ்டன்சஸில் த ஃபீல்ட் வில் பி ஈக்குவல் அண்ட் தட் the field will be radial everywhere. Since you have considered line elements of P1 and P2 in such a way that it turns out that the radial components are the only components that are present, since the other components are getting cancelled out each other. Hence the total field, okay fine. Finally, since the wire is infinite, electric field does not depend on the position of P along the length of the wire. In short, the electric field is everywhere radial. Great. That's basic conclusion. So now that we have a symmetrical configuration, I'm going to make use of this particular configuration to calculate the field. So let's consider an imaginary cylindrical Gaussian surface. Since the field is radial, flux through the two ends of the cylindrical Gaussian surface is 0. Right. So we'll have to consider only the area of the cylindrical surface that is radial, that is the curved surface area மட்டும் தான் கன்சிடர் பண்ண போகிறோம். ஸோ E is normal to the surface at every point and its magnitude is constant since it depends only on R. The surface area of the curved part is 2 pi RL, where L is the length of the cylinder. So the flux through the Gaussian surface is basically electric field multiplied by 2 pi RL. The surface enclosed charge equal to lambda L. Why is it a lambda L? Because we are considering a line charge which is having a distribution of lambda as the linear charge density and the length is L, and I'm considering only for an L part. L part consider பண்ணுறோம்னா the L part, though we are having an infinite wire, will eventually get cancelled. So basically the flux is going to be electric field multiplied by the 2 pi RL, and since everywhere it is perpendicular, which means that, I mean, it is along the surface, along the area vector, hence it's that, which is equal to lambda L by epsilon naught. The electric field due to this guy is going to be lambda L factor gets cancelled out, lambda by 2 pi R times epsilon naught, 2 pi R the whole, yes. So when n cap is the radial unit vector in the plane normal to the wire passing through the point, E is directed outward if the lambda is positive and inward if lambda is negative. Okay, fine. Note that when we write a vector A as a scalar multiplied by a unit vector, the scalar A is an algebraic number. It can be negative or positive. The direction of A will be the same as that of the unit vector A cap. If A cap is 0, greater than 0, and opposite to A cap, if A is less than 0. When we want to restrict to non-negative values, we use the symbol mod A and call it the modulus. So thus the modulus of A will be always greater than or equal to 0. Also note that though only the charge enclosed by the surface was included above, the electric field is due to the charge on the entire wire. Further, the assumption that the wire is infinitely long is crucial. Without this assumption, we cannot take E to be normal and the curved part of the cylindrical Gaussian surface. So இங்கே வந்துட்டு சில முக்கியமான அசம்ஷன்ஸ்லாம் என்னென்ன பண்ணியிருக்கோம், நம்ம பெருசாக ஒன்றும் இல்லை, இன்ஃபைனைட்லி லாங் வயர்னு எடுத்திருக்கோம். ஏன்னா ஒரு இன்ஃபைனைட் வயர்னால் அப்போ கண்டிப்பாக தேர் வில் பி அதர் காம்பனன்ட்ஸ் ஆஃப் எலக்ட்ரிக் ஃபீல்ட். ஸோ இன்ஃபைனைட் வயர்ன்ற காரணத்தினால தான் வி ஆர் ஹேவிங் அ ரேடியல் காம்பனண்ட் which is normal to the Gaussian surface, and we have considered only the charge enclosed in lambda L and the particular length, but still it is the electric field due to charge on the entire wire, since the L factor was not at all dependent upon the length of the wire, considering it was a infinite wire. So it's approximately true for electric field around the central portions of a long wire where the end effects may be ignored. So in the particular case, since we are having an infinite wire case, the end effects are ignored. Moving down, you have field due to a uniformly charged infinite plane sheet. So let sigma be the uniform surface charge density of an infinite plane sheet. We take the x-axis normal to the given plane. By symmetry, the electric field will not depend on y and z coordinates, and its direction at every point must be parallel to the x direction. So since I am having an electric field which is going to be in the direction perpendicular to that particular guy, the y and z components are going to be obviously considered to be 0. So we can take the Gaussian surface to be a rectangular parallelepiped of a cross-sectional area A. Parallelepiped, say right, okay. Cylindrical surface will also do. So as seen from the figure, only the two faces 1 and 2 will contribute to the flux. The other guys are perpendicular, which means that they are not going to contribute for the flux. And the surface charge density turns out to be sigma. Therefore, do not contribute to the dual flux. The unit vector normal to the 1 is minus x direction, while the unit vector normal to the surface 2 is plus in. Okay, therefore the flux E dot delta S through both the surfaces are equal and add up. Okay, so therefore the net flux to the Gaussian surface is 2 times EA. Okay, so the charge enclosed by the closed surface is sigma A. So 2 times EA is equal to sigma A. So E is sigma by 2 epsilon naught. அதாவது the field due to an infinitely charged uniform plane sheet வந்துட்டு it is considered to be sigma by 2 epsilon naught, not sigma by epsilon naught பா, சரியா? நம்ம கெப்பாசிட்டரில் பார்க்குறது வந்துட்டு sum of the both plates அதோடைய field. So electric field is directed away from the plate if sigma is positive, okay, and towards the plate if sigma is negative. Note that the above application of Gauss's law has brought out an additional fact: electric field is independent of x as well. So it is not at all dependent upon the distance. எங்கே போனாலும் அதே amount of electric field தான் அப்படின்ற சொல்லியிருக்காங்க. So for a finite large planar sheet, equation 1.33 is approximately true in the middle regions away from the ends. So as far as this particular guy is in the middleist region, that is away from the ends, this guy is approximately equal ன்னு சொல்கிறாங்க. So field due to a uniformly charged thin spherical shell. So let sigma be the uniform charge density of a thin spherical shell of radius r. The situation has obvious spherical symmetry, which means that the field at any point P outside the circle can depend only on the radial distance and must be radial only. Now that I am gonna try and find the value of so let's say there is I'm having thin spherical shell, which means the sigma is the amount of charge present, and let's say it has a radius of 4 pi capital R square. I mean the surface density. Since the electric field is going to be perpendicular at every point, it's going to be electric field multiplied by the surface charge density, that is 4 pi R square, which is equal to the net charge enclosed. The net charge enclosed will be equal to the surface charge density multiplied by the area. Correct? So இதில் மேட்ரு ఏంటిனா the electric field I'm going to calculate, the Gaussian surface which I've used is going to have some other value of R. Okay, it's not essentially capital R, it can also be capital R. For a general case scenario, I'm considering the small r which is greater than or equal to capital R. So which means that the 4 pi factor gets cancelled over here. The electric field is going to be sigma times R square by small r square. Sigma is basically Q by 4 pi R square by R square. I'm missing something, guys. Sigma by epsilon naught. Oh yeah, epsilon naught factor is actually missing, and R square factor gets cancelled, which means it's a Q by 4 pi epsilon naught times by R square. Yes, R square factor gets cancelled, and yeah, I have an R square. So it's a KQ by R square is the electric field due to a thin spherical shell outside surface, and KQ by capital R square will be the value of electric field on the surface. Now that we have both the cases, now we'll try calculating for inside the shell. So inside the shell there is no charge inside the shell, then obviously it's going to be 0 inside the shell. So an early model for an atom considered it to have a positively charged point nucleus of, okay, so the atom as a whole is neutral. For this model, what is the electric field at a distance r? Surrounded by a uniform charge density. Okay, so they are basically talking about okay, fine, great. That's a atom is a whole is a neutral. What is the electric field at a distance r? 4 by 3 pi r cube is volume multiplied by is equal to 0 minus ZE. Charge distribution for this model of the atom is as shown. The total negative charge in this uniform spherical shell is minus ZE, since the atom So on symmetry operations, we encounter systems with various symmetries. Considerations of those symmetries helps one arrive at results much faster than otherwise by a straightforward calculation. Consider, for example, an infinite uniform sheet of a charge, surface charge density sigma along the y-z plane. This system is unchanged if A translated parallel to the y-z plane in any direction, B rotated about the x-axis. So system is unchanged under any symmetry condition. So must its properties be. In particular, in this example, the electric field E must be unchanged. So translational symmetry along the y-axis show that the electric field must be same at a point. Similarly, translation symmetry along the z-axis shows the electric field at 2 points must be the same. By using rotation symmetry, must be perpendicular to y-axis, that is, must be parallel to the x direction. Okay. So we are having the summary over here. Let me just read it out once. So what's the summary? So basically, electric and magnetic forces determine the properties of atoms. For simple experiments on frictional electricity, one can infer that there are two types of charges in nature. That's like charges repel and unlike charges attract. The charge on a glass rod rubbed with the silk is positive, that on a plastic rod rubbed with the fur is negative. Conductors allow movement of electric charge, insulators do not. Metals, the mobile charges are electrons, and electrolytes, both the positive and negative ions are mobile. Electric charge has three basic properties: the quantization, additivity, and conservation. Quantization means that the total charge of bodies and an integral multiple of the basic quantum of charge E, which is equal to 1.6 into 10 power minus 9 coulomb. Additivity of charge means that the total charge of the system is the algebraic sum of the charges with the proper signs. Conservation of charges means that the total charge of an isolated system will remain unchanged with time. And Coulomb's law states that it is stated for a point charges, and the mutual electrostatic force of repulsion or attraction between them will be equal to kq1 q2 by r2 square r2 r square. And if I'm representing it vectorially, it is r21 square times r21 cap, and yeah, where k is a constant, arbitrary constant, which is equal to 909, and subsequently we'll express it with respect to the permittivity, which is having a value of 8.85 into 10 power minus 12 for vacuum, and the ratio of electric force and gravitational force is of order 10 power 39 for proton and electron. And superposition principle is the forces with which the two charges attract or repel each other are not affected by the presence of the third or okay fine. So for an assembly, okay fine, great. The electric field at a point is the force on a small positive test charge q. So basically it is the force experienced by a unit positive charge placed at a proximity due to the presence of a capital Q charge. Yes, it is radially outwards from Q if Q is positive. An electric field is a curve drawn in such a way that the tangent at each point on the curves gives the direction. The relative closeness of the fieldness gives the relative strength. Crowd near each other in regions of strong electric field and far apart where the electric field is weak. Regions of constant electric field, the field lines are uniformly spaced. Some of the important properties is that they are continuous curves without breaks, they do not form closed loops. For positive charge, the field lines start, and for negative charge, they end at negative charge. The two field lines cannot cross each other, and an electric dipole, okay, fine, we have certain expressions over here, and the torque is going to be the dipole moment multiplied by the electric field. If the electric field is considered to be uniform, the flux is going to be E dot delta S. Delta is an vector area element, okay fine, great. And then Gauss's law, the flux of an electric field through any closed surface is 1 by epsilon times the total charge enclosed. Okay, so thin infinitely long straight wire, okay, the electric field is going to be lambda by 2 by epsilon naught times r. For infinite thin plate, it's going to be sigma by 2 by epsilon naught. The electric field due to thin spherical shell on the surface is kq by capital R square, that is capital R is the radius, and away that is out of the surface is going to be kq by small r square, which is yes, and from inside it's going to be 0. That's all about it. And then we have certain conventions over here. The vector area element is delta S as the dimensions of L square with the unit meter square, and delta S, okay, vector is actually the magnitude of area element multiplied by the normal vector along when normal to that particular area. And electric field E is having dimensions ml d power minus 3 a power minus 1 as a unit of volt per meter, and electric flux phi has a voltmeter, that is E dot delta S. A dipole moment has coulomb meter, that is vector directed from negative to positive charge. And we have certain charge densities, linear surface and volumetric charge densities. Okay, we have certain points to ponder, and we have about 10 questions, 20, 30, 34 questions. Yeah, I think we can do them actually. It will not take much time. So you might wonder why the protons all carrying positive charges are compactly residing inside the nucleus. Why do they do not fly away? We learn that there is a third kind of a fundamental force called the strong force which holds them together. The range of the distance where this force is effective is about 10 power minus 14 meter. This is precisely the size of the nucleus. Also, the electrons are not allowed to sit on the top of the protons, that is inside the nucleus, due to the laws of quantum mechanics. This gives the atom's structure. Coulomb's force and gravitational force follow the same inverse square, but the gravitational force has only one sign. Okay, the constant of proportional decay is a matter of choice if the unit of charge is to be defined using Coulomb's law. So basically, however, what is defined in the unit of current here, its magnetic effect, and the unit of charge Coulomb is simply defined by 1 Coulomb is equal to 1 ampere second. And in this case, the value of k is no longer arbitrary. The approximately is a 9 power 9 Coulomb. The rather large value of k, the large size of the unit of charge from point of view, the electric effects arises because, as mentioned in point 3, the unit of charge is defined in terms of magnetic forces, which are generally much weaker than electric forces. Thus, while 1 ampere is a unit of a reasonable size for magnetic effects, 1 Coulomb is equal to 1 ampere per second is too big a unit for electric effects. Okay, so என்ன சொல்கிறாங்கன்னா k வந்துட்டு the larger size of the unit of charge from the point of view is electric effect, because the additivity of property of charges is not an obvious property. It is related to the fact that electric charge has no direction. Okay, charge is not only a scalar under rotation, it is also invariant from frames of reference on relative motion. This is not always true for every scalar. For example, kinetic energy is a scalar under rotation, but it is not variant for frames of reference in relative motion. So conservation of total charge of an isolated system is a property independent of the scalar nature of the charge noted in point 6. Conservation of total charge of an isolated system is a property independent of the scalar nature. Conservation refers to the invariance in time. So quantity may be scalar but not be conserved. On the other hand, can consider vector quantity like angular momentum. Quantization of electric charge is a basic law. There is no analogous law on quantization of mass. Superposition principle should not be regarded as obvious or equated with the law of addition of vectors. It says two things. Force on the charge due to another charge is unaffected by the presence of other charges, and there are no additional 3 body, 4 body, etc. forces which arise only when there are more than 1 2 charges. So the electric field due to the discrete charge configuration is not defined at the allocations of discrete charges. For continuous volume charge distribution, it is defined at any point in the distribution. For a surface charge distribution, electric field is discontinuous across the surface. The electric field due to charge configuration with total charge 0 is not 0. But for distances large compared to the size of configuration, its field falls off for types of or typical of field due to single charge, and electric dipole is the simplest example of this fact. Okay, so now we can enter into the exercises. Yeah, we'll do. So what is the force between two small charged spheres having charges 2 into 10 power minus 7 coulomb, 2 into 10 power 3 minus 7, 3 into 10 power minus 7 coulomb, placed at a distance of 30 centimeter. So basically, let's get started with the first question, the additional exercises. So the force is gonna be 9 into 10 power 9 multiplied by 3 into 10 power minus 7 into 2 into 10 power minus 7 divided by value of distance is 30 into 10 power minus 2 the whole square. So it's a 9 3s are 27 into, let's have it as 27 itself, into 2 into 10 power minus 14 into 10 power 9 is a 10 power minus 5 factor. 10 power minus 5 into 10 power 4 is a 10 power minus 1 factor. 10 power 4 okay, that divided by 330 square, it's a 9 into 10 power 2 factor. So which means that we have a 3 into 2, that's a 6 into 10 power minus 3 Newton amount of force. Moving down, the electrostatic force on a small sphere of charge 0.4 microcoulomb due to another small sphere in air is 0.2 Newton. What is the distance? What is the force on the second sphere due to the first? So if the first sphere has a force of 0.0 Newton, obviously the second sphere, I mean like the Coulomb's law, I mean the charges actually obeys the Newton's laws, that is the third law. If one charge exerts a force of 0.2 Newton on the other charge, then the other charge will also exert exactly the same amount of force on the first charge. So it's going to be 0.2 Newton in the first place. Now we'll talk about the first question. So what they have given is that 0.2 Newton is equal to 9 into 10 power 9 multiplied by 0.4 into, let's consider only the magnitudes for now, into 10 power minus 6 into 0.8 into 10 power minus 6 divided by the distance. That's what we will have to calculate now. So it's 9 into 9 4s are 36 into 0.1, that's 3.6. 36 into 8, it's a 4, no, it's either 48, 4, 8 3 is a 24, 288, it's a 2.88 factor. That multiplied by 10 power 9, 10 power 9, 10 power minus 3 by r square. 0.2, 0.1 into 1.44. So r square is equal to 14.4 into 10 power minus 3, which is 1.44 into 10 power minus 4. So r is equal to 1.2 into 10 power minus 2, that is, it is 1.2 centimeters away. Moving down, check the ratio, look up a table. Okay, what does the ratio signify? Physical constants, and determine the value of this ratio. So basically Ke square by J me mp shows that the ratio of forces between proton and a neutron, that is the ratio of its electrostatic forces divided by the gravitational force, and it turns out that its value is 2.4 into 10 power 39, and it shows how strong an electrostatic force in front of a gravitational force. It is about 10 power 39 times the value of a gravitational force. So now that moving to the next question, explain the meaning of the statement electric charge of a body is quantized. So what they're trying to say is that It means that the charge in a body is actually an integral multiple of the basic fundamental charge defined as E, whose value is equal to 1.6 into 10 power minus 90. So why can one ignore quantization of electric charge when dealing with macroscopic system? So basically, in case of macroscopic system, the discreteness in the charge is not that visible, which means that only in case of discrete charges, where I'm like dealing with very small, that is very minute amount of charges, I will have to consider the quantization of charges. At a macroscopic level, let's say I'm dealing with a 10 microcoulomb of charges, which is actually 10 power 13 times the actual value of charge. So in such case scenarios, the quantization is not going to be that useful, which means that it can actually be ignored. So when a glass rod is rubbed with the silk rod, charge appears on both. A similar phenomenon is observed. Okay. Explain how this observation is consistent with the law of conservation of charge. So according to law of conservation of charge, in a given system, a charge is neither created nor destroyed. So in case when glass rod is rubbed with a silk cloth, the glass rod has certain electrons which is actually transferred to the silk cloth, and rather than it's actually transferred and not created newly. So only the electrons that was present in the glass rod is actually transferred to the silk cloth, which means that the transfer of electron does signify that it is consistent with the conservation of charge. So 4-point charges, okay, 2 minus 5, okay, are located at the corners of what is the force on a, okay, fine, great. It's actually simpler. I'm not going to calculate it. It's actually, the calculation part is going to be too long, okay. Moving down, an electrostatic field line is a continuous curve. That is, a field line cannot have sudden breaks. Okay, why does not it have a sudden break? So basically, the electric field lines are symbolizing the force that's acting on a particular place or a particular position. So if in case I'm changing the position, I mean like at a particular place it breaks, it means that on the particular place it force on act agalன்ற which is insignificant, because we have the force is actually an inverse square law which varies with respect to distance. Though it might diminish to a smallest value, still it is consistent, it is continuous, which means that it's not gonna be breaking at any moment. Hence the electrostatic field will also not break, and that the continuous curve will not break. Explain why two field lines never cross. So basically, electric field line signifies the tangent to electric field line at each point signifies the direction of electric field, and if at all there is a crossing occurring, then there cannot be two values of electric field, net electric field direction at a single point, and that's why there cannot be two field lines crossing each other. Moving down, we have 2-point charges, okay, located, fine. What is the electric field at the midpoint of the line AB? So basically, we'll have to make use of the principle of superposition. We'll have to basically add them. Yes. If a negative test charge of magnitude 1.5 into 10 power 9 is placed at that point, what is the force? So first of all, we'll have to calculate the field, and then we'll have to multiply it with the value of the test charge. A system has two charges. Okay. What are the total charge and electric dipole moment of the system? So total charge is 0. Yes, and I'll have to find the electric dipole moment. That's actually 30 multiplied by 2.5 into 10 power minus 7. 30 centimeter is actually 30 into 10 power minus 2. That's a 0.3. 0.3 multiplied by 2.5 is actually 0.75. That's a 7.5 into 10 power minus 8 electric dipole moment. So an electric dipole moment is given. It is aligned at 30 degree, and we'll have to find the torque. Torque is actually the value of dipole moment multiplied by, that is 4 into 10 power minus 9. That multiplied by the value of electric field, that is 5 into 10 power 4. So basically it's a 20 into 10 power minus 5. That's a 2 into 10 power minus 4. That multiplied by sin theta, it's actually a 10 power minus 4 factor. Polythene piece rubbed with wool is found to have a negative charge of this. Estimate the number of electrons transferred. So basically the number of electrons transferred will be the total charge divided by charge of one electron. So it's a 3 into 10 power minus 7 divided by 1.6 into 10 power minus 19. So 3 divided by 1.6, let's take it roughly to be 2. So it's a 2 into 10 power minus 19, that's okay, that's 10 power 12. So that's about 2 into 10 power 12 approximately is the transfer of mass from wood to polythene. uh, it does not have any significance, but yes, actually there's some amount of mass that's being transferred. Then moving on, two insulated charged copper spheres A and B have their centers separated by a distance of 50 centimeter. What is the mutual force of electrostatic repulsion if the charge on each is 6.5 into 10 power minus 7 coulomb? Those are two insulated charged copper spheres, okay, separated by a distance of 50 centimeter. Okay, mutual electrostatic repulsion. Okay, fine. The radii of A and B are negligible. Okay, fine. This is actually usage of Coulomb's law. What is the force of repulsion if each sphere is charged double the above amount? And distance between them is half. So distance between them is half, then actually the force will become 4 times, and since both of them are halved, then obviously it will be unaltered. Suppose the spheres A and B in exercise 1.12 have identical sizes. Third sphere of same size as sun charge is brought in contact with the first, then brought in contact with the second, and finally removed from both. What is the new force of ஓகே ஸோ ஃபஸ்ட்டு வந்துட்டு என்ன சொல்கிறாங்கன்னா, ரெண்டு ஸ்பியர்ஸ் இருக்குப்பா. ஸோ ஃபஸ்ட்டு ஸ்பியரில் க்யூ இருக்குது, இன்னொரு ஸ்பியரில் க்யூ இருக்குது. இப்போது ஒரு அன்சார்ஜ் ஸ்பியரை ஃபஸ்ட்டு ஸ்பியரோட காண்டாக்டில் கொண்டு வந்தேன்னா, ஃபஸ்ட்டு ஸ்பியரில் Q/2 சார்ஜ் இருக்கும், செகண்ட் ஸ்பியரில் Q சார்ஜ் இருக்கும், அண்ட் தேர்ட் ஸ்பியரில் Q/2 சார்ஜ் இருக்கும். இப்போ இந்த Q/2 சார்ஜை வந்துட்டு ஐ எம் பிரிங்கிங் நியர் டு த செகண்ட் ஸ்பியர் அப்படின்னா, இட் வில் பி Q + Q/2 the whole divided by 2. It is a 3Q/4 amount of charge. That is 3Q/4 அப்படின்ற amount of charge will be present in the second guy, which means that the net charge will be actually become 3/8. So net force will become 3/8 of what the force was initially. Shows tracks of 3 charged particles in a uniform electrostatic. Give the signs of each. They are asking only the signs of the charge. So 1 and 2 are actually attracted towards positive sign, which means that both will have a negative charge, whereas 3 will have a positive charge. And they are asking which particle has the highest charge to mass ratio. So more is the mass, lesser is the deflection. So which means that 2 is having more mass, I think. Yes. Consider uniform electric field. What is the flux of the field through a square, okay, whose plane is parallel to YZ plane? What is the flux through the same if the square is okay, it's easier. Okay, fine. Careful measurement of electric field at the surface of a black box indicates that the net outward flux of the surface is this. And what is the net charge? So if flux is given to be that, then I will have to multiply it with epsilon naught to obtain the net charge. So if the net outward flux through the surface of the box was 0, could you conclude that there were no charges? So yeah, basically net outward flux is 0 na, the net charge enclosed will be 0 அப்படின்றத சொல்றாங்க. Why is it so na? Why? This actually consists actually I'm not sure. That's actually inconsistent with the Gauss's law, but according in definition with Gauss's law. So let us just once refer what they've said over here. Okay, basically I will have to give an example of a particular surface, a general surface, and then I will have to say that it's inconsistent with what it is in, as we have seen in Gauss's law. So point charge +2, okay, placed above the center of a square of side 10 centimeter. What is the magnitude of electric flux to the square? So basically that's the Q/epsilon naught is equal to E dot delta S, and delta S is here, Q is okay. Thank you. So what is the magnitude of the electric flux through the square? So basically E dot delta S is equal to Q/epsilon naught. Yeah, I don't think we need anything else. A point charge of 2 microcoulomb is at the center of a cubic Gaussian surface. What is the net electric flux through the surface? Through the surface. So it's basically cube epsilon naught. That's it. A point. Okay. Wait, they are asking the electric flux only. Yeah, okay, fine. Point charge causes an electric flux this to pass through a spherical Gaussian surface of 10 centimeter radius centered on the charge. The radius of the Gaussian surface was double. How much flux would pass through the surface? If the radius of the Gaussian surface were double, how much flux would pass through the surface? What is the value of the point charge? இருப்பா ஒரு நிமிஷம். Okay, so let's see what they have given over here. Estimate the radius of the drop. Oil drop of 12 excess electrons is held stationary under a constant free. So which means it is held stationary. Millikan's oil drop experiment. The density of oil is 1.26 gram. Oh my god. Which among the curves shown in the figure 1.35 cannot possibly represent the electrostatic? Oh. So C is fine. Yeah, D cannot be because it's intersecting. Yes. So in a certain region of space, electric field is along the z direction. The magnitude of electric field is however not constant but increases uniformly along the positive z. Having a total dipole moment. So electric field is increasing uniformly. Okay. So let's just end this session and continue this after some time. Yeah. We'll do the additional exercise after some time. Okay. Bye bye.